thanks a lot to the organizers for asking me to come to the school. It's really nice to be here, and thank you for being here in the morning, last day of the school. I guess that you are all a bit exhausted by now, perhaps. So let's see how we are going to go through this last tutorial or lecture. So since there are no speakers' introductions, and I completely agree with that, I copied Anna from yesterday, and I decided to introduce myself a little bit. You can read all this on my website, but I thought it would make sense to just say a few words about me. So, so I'm originally from Barcelona, from Spain, from Catalonia. And I did my PhD in London, in a computer science department, on computational linguistics. And then I did a couple of postdocs in Potsdam in Germany and at Stanford in the US. And since around 15 years, I'm a professor at the University of Amsterdam. Right. My background is in computational linguistics, NLP, computational linguistics, and cognitive science. So I'm not a computer scientist, I'm more a linguist, computational linguist. And I'm very interested in aspects that have to do with human cognition and how we can model that computationally. And that's a little bit where the driving force of my research into NLP. And I have a general interest in language use in communication, right? So that's maybe another way of saying in dialogue, in conversation. So not so much on how language is used in documents, let's say, which can be interesting for other purposes, but on how we use language like for interacting and for communicating with each other. And this is a bit what brings me also to multimodality, because I consider that language use is really shaped by social interaction, but also by how we relate language to the world, so by perception as well. And here is where multimodality comes in. Okay, and so I also wanted to highlight that I don't only work on multimodality, I work on different NLP topics. Like some of the topics that I'm currently working on in my group, that my PhDs and my postdocs are working on, are listed here. Like, for example, uncertainty is one of the topics, visual grounding, of course, as well, a lot on evaluation, both of text-only models and also multimodal models, and also on using language models for questions that have to do with human cognition, a bit like computational psycholinguistics. So I really like this link between how computational methods can help research in human cognition, and the other way around, how ideas from linguistics and human cognition may provide insights for NLP as well, all right? But in any case, today I will talk about multimodal NLP. I'm just telling you all this because I'm very happy to chat about any of this after the lecture with any of you. And from any of these, I mean any of these research topics, or including how I moved from postdoc in different countries to professor in another country. So anything that you find interesting and that you want to chat about, then I'm available for a few hours, because there are not that many hours left of the summer school. But anyway, so welcome, and I hope we'll go through this almost 3 hours. So we are going to talk about multimodal models, and of course this can mean many things, and I'm not sure exactly what expectations you have. Also, I realized that some of the speakers, like Andonis and Anna and so on, kept saying, Raquel is going to tell you all about this and all about that, right? So of course I'm the last lecturer, so yeah, I'm supposed to talk about everything else that they didn't have time and so on. So I'm afraid that I may not just fulfill all your expectations, okay? So multimodal models could be many things. In general, we talk about multimodal models as models that process at least more than one modality. And what are modalities? Well, are different means of conveying some information, of transmitting some information, right? And this means these modalities might be text, speech, images, videos, but also other perceptual stuff as well, like smells, sounds, actions. Code can also be a different modality. So there are tons of possible modalities, and as you may know, a lot of work in, well, machine learning, deep learning is actually trying to include these modalities, but today I'm going to focus on language and vision, so maybe a bit more classic if you want, still super interesting in my opinion. But this will be the scope. I will talk a little bit about speech towards the end, but not really, not much, right? So that was your expectation, then I can give you some references perhaps, but this will not be included in the lecture. So I'm gonna focus on the interplay between language and vision, and I will do that, not surprisingly, given the scope of the school, from an NLP perspective, meaning that not so much from a computer vision perspective, which of course would also be very relevant, right? But I'm an NLPer, so I will do this from a more language-related and NLP perspective, all right? So I hope that we are ready to get started. So first I wanted to ask you, why should we be interested in multimodality, meaning vision and language in this case, but you can take the question more generally if you want. So why is this, well, interesting or desirable? Is it desirable? I don't know, for NLP systems, or is it something, why should we pursue this? Are there good reasons for it? Maybe some of this has come up a bit in some of the discussions so far, right? But tell me a bit what your ideas are of why is that important?
I mean, different modalities convey different forms of messages. So if you restrict yourself to only one of them, you just might lose important information about the system you want to model.
Okay. So more modalities, more information. If we don't include them, we can maybe lose some stuff that is important for whatever we want to model, right? That makes a lot of sense. Anything else?
Because we want to believe in AGI.
Okay, can you elaborate a little bit? Because you're making the assumption that somehow intelligence is related to multimodality then, or, okay. All right, anything else? Yep.
I would say, in this case, I assume that one modality would be language, right? So via language, we can describe certain aspects of an image. So we are moving away from the standard labeling scheme that we might have with non-interpretable labels, and using the language to convey messages that cannot really be on a discrete space of labels, etc. So we can use language not just as a modality, but as a way to describe images, for example.
Okay.
For generating.
Okay, so if I understand you correctly, it's a bit that you can sort of like decipher what's in a kind of translate an image into another type of representation that we can very easily comprehend and so on, something a bit like that. Okay. All right, I think that all this makes a lot of sense, right? And this is a little bit also part of the reasons why I think that multimodality is interesting and it's worth pursuing. And a related kind of reason, I think, is because, well, so language is a human ability, right? And language is something that kind of allows us to construct meanings and to kind of have conceptual information, right? To encode conceptual information, right? And there is a lot of evidence that this is actually something multimodal in humans. And if we are modeling language, which is a human capacity, and we want our systems to be used by humans, then I think that the closer that we are to how humans construct meaning and represent language, then in principle that should be useful, right? So yeah, so human conceptual representations are multimodal. As I said, there is quite a lot of evidence for this. And you may have heard about the symbol grounding problem, right? Maybe some of you have heard about that. Not many, but some, okay, right? So yeah, so the idea behind the symbol grounding problem is that, well, how can we actually assign or acquire meanings for symbols like words, right? So words are symbols by themselves. They don't mean anything. They are just a bunch of symbols that are arbitrary, and we assign to them some kind of meaning. But how can we do that without actually having some system that links these symbols to external reality? So we need to ground these symbols not only to other symbols, as we do when we do text-only models, right? But arguably, at least, there is some extra linguistic information that we need in order to ground symbols, particularly those that refer to stuff in the world, right? And there is a lot of, this is more philosophical discussion on whether meaning can exist otherwise, can meaning really exist otherwise. So of course, we can learn a lot of meaning by just looking at co-occurrences, right? So we know, because we know that our systems work like this, right? We can learn word embeddings only from text, and they are actually very rich, and we we acquire a lot of like relations between words that provide a lot of meaning, but possibly that's not enough, right? So we also need to ground some of this meaning in external reality to have other features that, for example, come from visual information, right? So a typical example of bananas is that, for example, we may learn from text that bananas are high in potassium, that maybe sometimes they come from Costa Rica, that they are a fruit because of co-occurrences, but not very often we will encounter in text something that says that a banana is yellow, right? Because that's an obvious thing that we acquire by a perception, and that's not so commonly represented in text. So this is much more easily acquired by having experience of a banana in the actual extra-linguistic world. Right. Okay, so this idea of symbol grounding problem, that meaning, at least a part of meaning, must be related to how we establish a connection between words and the external reality. There is also evidence that comes from what's called embodied cognition, right? And this is a more neurological evidence saying that when we act, for example, when we move our fingers or when we move our feet or when we move our body, there are certain areas in our brain that get activated, and there is evidence that when we are reading about the same kind of things, right? So we are passively reading, we are not grasping something and so on, but we are just reading about grasping, actually similar brain areas get activated as well, right? So that what cognitive scientists conclude from this, or neuroscientists conclude from this, is that the conceptual representations that we have actually are multimodal. So they contain information that is not only symbolic, but that also relates to how we connect that meaning to our body, to what we do with our body, right? So this is evidence from neuroscience. Embodied cognition. So basically, quite a lot of evidence that human conceptual representations are multimodal. Maybe this is not very strong evidence for wanting to have also language, like NLP, language representations multimodally. It's just a piece of information that I think is interesting, right? In the same line, it's in terms of how humans represent conceptual knowledge, it's not only conceptual representations that are multimodal, but also how we perceive language, right? Is anyone familiar with this kind of test or this effect from speech, maybe? Speech people are, yes, right? So this is more about how we perceive. So the idea that we can have interference between modalities, right? So that what we are seeing may interfere with what we are hearing. So I will just play this video, if I manage, very briefly. And what I will ask you is that you try to, for a bit, just listen to the video with your eyes closed, so don't look at this woman who will articulate something, and then sometimes just open your eyes and then look at the woman, and then see whether you perceive things differently or
Okay, here we go. Baba, 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 Baba.
I'm not going to play
Baba.
it fully, but
Baba.
is something happening? not to some people, okay. Is something happening to someone?
With my eyes closed, it's Baba, but with my eyes open and seeing her dog, it's Dada.
Okay, so did someone experience a bit this? So if you, I just play it a little bit more, maybe now with your eyes open, perhaps, maybe start with your eyes open.
Baba, Baba.
So what do you hear when the eyes, when you are looking at her articulating?
Definitely not Baba.
Okay, I think so, right? So maybe it's a bit difficult. Right, well, the sound that is being actually played is Baba with a B, right? But when we are, actually, now that I was looking at her, it was completely crystal clear for me that it was that one, and that's what has been recorded. But then she is not articulating Baba because she's not closing her lips, right? So she's not articulating that. Therefore, when we are looking at her, and the fact that she may not possibly be articulating Baba, that interferes with what we actually hear. And we don't hear Baba, we hear something else that can be Tada or Dada or something like this, but not something where the lips would be closed, right? So what we are saying is actually interfering with what we are hearing, even though there is a ground truth hearing, which is the baba syllable. All right, so just more evidence that there is a lot of cross-modality and multimodality on how we represent meanings, but also on how we perceive information that have to do with language, in this case with speech. So just more along the same line from the NLP community, I don't know if you saw this paper that came up, well, now already 4 years ago, actually, by Biscuit et al., which was articulating ideas that actually had been around for a long time, but it was just making this point that, that language is really tied to experience, like broadly understood, and that this experience is multimodal, and that therefore, if we wanted to advance NLP more generally, that we should move toward approaches that take more into account this link to experience between language and experience, right? So the idea is that you cannot fully learn language, whatever that means, this idea that language is multimodal, etc. You cannot fully learn it if you are just listening to the radio or reading books, right? So this would correspond to the corpus methods, right? Where we are just corpus methods, meaning text-based methods, right? By this, you cannot really learn fully language, but that's how many of our systems do learn, right? You can also not just do it by watching television. So even if you just add images, in fact, that would not fully work. So the kind of vision and language that I'm going to present here is a step forward, but it's not something that is going to account completely for the link between language and experience. Right, and also you cannot fully learn language without communicating with others. So the social aspect of using language for a purpose, right, to achieve something for some goals in the world and with others, this is also fundamental to what language is, right? And I'm not even going to talk about that, even though that's fundamental part of my research. Tell me.
Yeah, although there is some truth to that, it kind of contradicts how blind people can still learn language perfectly well.
Yeah, but of course, because vision, so of course we can have different, we can be challenged for different modalities, but we will most people, right, the large majority will have some sensory possibilities, right, and the possibility to interact with others. So of course, like blind people, obviously can learn language, deaf people can learn language, so that's not a problem, right? So that's why, so here we are using the example of watching television, but it's more, you need some sort of perception and you need some sort of embodiment. The more restricted that you are, the more difficult that it will be for you to develop conceptual representations that are similar to the community you are integrated in, right? So this does not assume that you need to have good vision. Does it make sense?
So could we say that we can learn more efficiently with more modalities, but we could still
That's
learn
a good point.
without some of those?
Well, that's a good point. I mean, some people will make the argument, and I think that they tend to, sorry, do you hear me if I'm not there? Yeah, so that some people will argue that you cannot really learn language as we understand it properly and as we use it, right? That is not only a matter of efficiency, but it depends about what we are after, right? So it depends what our goals are. Maybe, when we are trying to learn language that is useful for certain applications, we also don't aspire maybe to AGI, right? So that depends what we aspire to. There is some recent work that shows, for example, that indeed multimodality helps you in efficiency. But in the long run, if you have tons of data, it may not help you. But that depends on what is your evaluation measure. What is it that you are measuring that you are learning, right? If you are learning just vocabulary. So.
No, but even the first LLMs were trained only on text.
Mm-hmm.
And it seems they excel in language, basically.
Well, yes, but they also have a lot of problems. Yeah, okay, but I think, they are very impressive, but that doesn't mean that they don't fully have problems, right? I think we saw many of the problems pointed out, for example, in the lecture of yesterday and in other lectures. So they are amazing, but it's not that they cannot be a bit better when it comes to actually representing language.
But those problems that we have, one can argue, are reasoning problems, not language.
Maybe, yeah, maybe. So I think this is a debate that I'm not going to solve here. Like, do we need multimodality to have better language models? Well, I don't know. I think that we don't have solid evidence for saying, yes, we need it, right? So I think we don't have solid evidence for that. There are other reasons why we may want to include multimodality, and here's what I was trying to get out of you at the beginning. I think, yes, I think that that's closer to how humans are, and of course, it allows us to tackle tasks that are multimodal, right? So if you want to be more practical. But I agree that we don't, I would not directly say, yes, we need multimodality to achieve better models, I think.
No, I wouldn't take that, but I would definitely need multimodality for better models. But to master language alone, maybe that, and I'm not against multimodality.
Yeah, okay, but, right. Well, anyway, I think we're going to continue. But I think, for me, language is really actually multimodal. So I think that even for learning language, multimodality is very important. But we could disagree with this, right? So, yeah, so from a more practical point of view, of course, multimodality can help us to reduce ambiguity that is present just in language, right? So if we have... so language can be ambiguous in many different ways because of possible different structures that we may assign to sentences, but also, of course, because of possible different meanings of words. And obviously, if that is paired together with a context, with a visual context that disambiguate what's going on, then obviously that's going to help us, right? And as I was saying before, basically, there are also many useful applications that are multimodal that we may want to develop, and I'm sure that you have some in your head, but multimodality can increase accessibility for different people, for example, for visually impaired people, if we may be able to describe what's going on in a video or to describe what's going on in an image. It may allow us to develop robot assistants that actually act in the world and do things in the world, describe what they do, and many other like kind of sky-high applications, right? So even in that sense, I think it's clear that multimodality is useful, and I think you already gave me several. Well, it's desirable, and you already gave me several reasons why we may want to have it, right? So I gave you a little bit more the cognitive reasons of why multimodality really is involved in human language processing and how that can be a motivation as well. All right, so this is the plan. Let's see if I will manage, because I think we're going to go a bit slowly, but anyway. So before the coffee break, I would like, if possible, to talk a little bit about like main approaches, like data sets and modeling techniques. So the modeling techniques and the data sets that are required to develop this, like the main tasks that have traditionally been tackled in vision and language, and the kind of models that have come up over the years on these kind of topics. And we'll look at two types of approaches, like task-specific approaches, so approaches, models, and data sets that were designed for tackling specific tasks, for example, image captioning, and so on, and then more general-purpose models, like pre-trained multimodal models, right? And then in the second part, if we manage to finish this part initially, then I want to discuss a little bit possible ethical issues regarding multimodal training data, which maybe apply also to text, but with multimodality, they are also present. So I'd like to discuss this a little bit. Then evaluation with respect to the tasks and models that we have seen in the first part. So what kind of methods for evaluation and what kind of challenges we encounter for evaluation. And at the end, I'd like to present to you some new direction. I call them new directions. They are not necessarily super new, but slightly different directions from the ones that are pursued in more mainstream NLP that have to do with vision and with language. Okay? So I hope that sounds fine. So we'll go ahead. Right, so the general trend in the approaches in vision and language is very similar to what probably you have already seen for text-only NLP, right? So initially, the type of approaches that were proposed were really task-specific, right? So for example, let's have a system that is able to describe images, like an image capturing system. And for that, we will develop a data set that allows us to train such a system, and then we will devise an architecture that then can be trained in a supervised way for achieving that task, right? So task-specific approaches. And the classic tasks are image captioning, visual question answering, and other related tasks that I will show you a couple of examples. And from this, we have been moving to more general purpose task type of data sets that in principle are pre-trained in a task agnostic way, right? So, and sometimes we call them foundation models, but not very clear exactly what this term is covering, right? But the idea here is that we pre-train him for learning good representations, and then we may fine-tune them for the tasks that I mentioned here. Maybe we will fine-tune them for this task, or we will use them in different ways. Right? But the point is just to learn good, robust, multimodal representations, visual and language representations, right? So I suppose that you are seeing the parallels with what you have been seeing in text-only NLP in this trend as well, right? Okay, so let's go with these task-specific models, and yeah, as I said, we'll see a bit what are the data sets, what are some of the main architectures, and what are some of the main tasks. And here, initially, this is trained. These models are developed with supervised learning on these specific data sets, right? So we will see the models and the tasks at a rather high level. Some of them will, I think, ring bells from things that you have seen in previous lectures, so I hope that you can get a general idea, and there are always references that you can go to have more details. So there are many types of tasks, right? So I mentioned already, like image captioning and visual question answering, and some of these tasks can be operationalized as image condition text generation, right? So remember that this was also mentioned by Adonis on Monday, right? So where, for instance, in machine translation, we have text condition like encoder-decoder models where we are conditioning text on text. So here we can think of this as image condition text generation, and that would be, for example, image caption or video description, or also visual storytelling, where we have a sequence of images and we want to produce a story in language for those images, right? Other tasks like visual and question answering are sometimes operationalized as classification tasks. We'll see why it might not be justified, actually, and there are some approaches that, of course, with generative models are moving towards more natural language generation. But originally, this was operationalized as a classification task, similarly with visually grounded reasoning, and other tasks are more related to ranking and alignment, like, for instance, image retrieval or text retrieval from images, and so on, right? And there are many, many more tasks that people come up with. Some of them are more useful than others, perhaps, but people just come up with tons of tasks, and we are not going to see them all, right? But I don't know, visual entailment, of course, image generation. I'm not going to talk much about image generation, so it was actually very nice to see Aida Nemadzadeh's talk yesterday afternoon, because she already delved directly into multimodality and multimodal models, so that was a kind of a good introduction for this lecture, and she talked a little bit about image generation and so on. I consider it more a computer vision type of task, and I will not cover here, even though I know that it's very popular, and maybe you're very excited about it, but I will not cover it here. So there are tons of tasks that are possible and that people have tried to tackle, right? So, of course, the main point that unifies all these tasks, that's why I'm presenting this here, is that they involve combining information from language and from vision, right? That's why they are multimodal tasks, and in this case, language and vision, which is our focus, right? So, maybe the main question that we should try to look into is how we should represent visual information. So we want to combine vision and language information. Over the last few days, definitely you have seen how we can learn text representations, right? So how we can learn word embeddings and other types of representations. So we have a very good idea in NLP how to learn text representations. But so how do we represent information from vision, information from other modalities, and in particular from vision? Of course, it looks like we have to probably go into what computer vision researchers do, right? There's no way around it. But initially, in NLP, like very early approaches, you know, like in the 2010s or something, then it's not that people were not looking at grounding, right, at visual grounding. For instance, for the task of referring expression generation, for instance, imagine that you want to refer to one of these images there, to one of these characters here, right? You want to refer to it, and you want to make sure that your referring expression really identifies this individual here with respect to the other individuals in the context, right? So you need to use information about this referent, which is extra-linguistic, right? But in early approaches in NLP, we would just not have the tools to directly represent the visual information. So what would we do? We would just represent that entity, that extra-linguistic entity, with some sort of logical form, right? With some sort of symbolic representation. So here you can see how we can describe that individual, right? And then the task would be, well, from this symbolic representation, how do I have a system, how do I develop a system that then generates a referring expression, like, for instance, the person with a light colored beard or something like that, okay? So in those years, the focus was on this mapping here, the mapping between this symbolic representation that would be given, it would be annotated, it would be given into some language description, right? So, of course, as computer vision methods were developed further, then we could take up information, we could take get research from computer vision, and then the focus shifted towards the other mapping, how we can learn to represent directly visual information, right? So then it's not going to be a symbolic representation most of the time, even though sometimes it can be symbolic, like a scene graph or something like that, right? But most typically, now we want to look at the other mapping. From the visual information, some other type of representation that then we can combine with language, right? So we want to automatically learn these representations that more typically are going to be sub-symbolic, like vector representations and so on, that then we can easily combine with language, right? So this was stuff that was happening in computer vision, and the early computer vision models, they were all trained on object recognition, and that was done thanks to the ImageNet data set, right? So a large data set that was developed actually before 2010, and then it kind of started, it grew over the years. It was developed by Fei Li. And this is a dataset, as you can see, as you can read here. So it's an image database organized according to the WordNet hierarchy, right, which I guess you're familiar with, and where each node is depicted by hundreds and thousands of images, right? So for each node, for each concept in WordNet, for each word in WordNet, then we have tons of images associated with them, right? So this was not, from the computer vision community, this was not considered language and vision, right? So these were concepts, not language. So the labels were conceptual labels, and the point was, let's try to learn how to map images to these kind of concepts, right? So using this kind of data, then, and with the deep learning revolution, with the possibility of having deep neural networks, then the initial approaches were using these convolutional neural networks pre-trained for this task of object recognition using this large ImageNet data set, right? So I think, did you see already convolutional neural, did you see CNNs at some point? Was it in the first lecture, or? Not for images, but can you tell me a bit in which context did you see it? How did it work for text? In which, if you remember?
Because when talking about NLPs, I think Ryan said that you could slide an NLP on top of fragments, anchors, and in fact it carries what you have.
Okay, all right. All right, okay. Well.
It was for merging word embeddings, applying it on word embeddings and aggregating their meaning or averaging the meaning of word embeddings. Like
All right. Okay, yeah, all right.
One-dimensional instead of two-dimensional.
Yeah, exactly. That's what I'm thinking. So probably you would apply the filters one-dimensionally, sequentially over text, and so on. Right. So if we have a CNN of a vision, right? So then what we start is with the numerical pixel values of the image, right? And then we apply filters of different size over this to the representation of the image, right? And so I think that, well, this is a very schematic representation, but yeah, so the main initial, well, not initial, anyway, so this would apply to the VGGNet and to ResNet as well, but basically, so you start from the pixel representations and then several convolutional layers, followed by some ReLU activation and some max pooling, that what they are doing is kind of make the information more dense and more abstract, right? So we are just capturing the important information, in principle, retaining the localization of where this information is in the image, right? But the dimensionality of this image gets reduced progressively over the convolutional layers, and you can see a bit the schematic depiction here, abstract depiction of what is the information that is being retained as the network learns more abstract representations over the different layers, okay? And then, yeah, so this network in the end is trained for object recognition. So there are a couple of fully connected layers at the end, and then finally a softmax function that has as the possible outputs all the classes of the objects that are available. So now I'm not sure whether it's really all the classes in WordNet or a restriction for a particular class, a particular subset or something like this, right? But this is how the network is trained. So it's trained to learn useful representations that directly come from the pixels that allow it to figure out what's the concept that is being present in that image. That allows it to identify what are the objects, to identify what are the concepts, right? And then so from this type of neural networks, different kinds of features towards the later layers are the ones that we can use to then combine with language. And we can use the pooled features at the end, so before the classification layer that corresponds to a vector, but sometimes also the last feature map that still retains some local information, right? So that would be a set of vectors here. And different approaches just use slightly different types of visual features from this network, but they all are layers that have already acquired this kind of abstract knowledge. So from this kind of just pure CNN learned representations where we are processing the entire image and just abstracting over all the patches in the image, a next type of approach was like, well, why should we treat all the regions of the image in the same way? So of course the CNN is supposed to learn what's the important information, right? But maybe we can give it a bit of a push and first try to determine what are the kind of entities that are important and that are present in this image, right? And then work with that, right? So these were an additional set of neural nets that were developed, a kind of follow-up of the plain CNNs, right? So R for regions, and then so the network here. Yeah, so sorry, this would be the one at the bottom, right? So the one at the top would be more standard CNN. So if we have the feature map from each of the regions in the final map, we could extract a vector, right? But with the object regions, what we would have is we would have an intermediate network for region proposals that would try to identify what are the salient objects there. Right? And then this would give us some bounding boxes for the salient objects, and to this particular region, we would apply the same CNN convolution, so the same type of convolutions, right? But not to arbitrary patches in the image, but just to the ones that actually contain entities. Okay, so it's a little bit more refined, a little bit more targeted for actual entities. To be able to do this, it's not sufficient to just have ImageNet with all the categories associated with a general image, but something that annotates images at a more fine-grained level. And that's the visual genome data set, which you can have here. So it's also based on WordNet, but the annotation is more at the object level, right? So there are bounding boxes, and then people were characterizing what are the different objects and what are the relations also between the objects that are present in the image. So this provides additional information and an additional learning signal that can give you more fine-grained type of visual representations. All right, so these were the initial CNN systems. They are still used in different kind of models, but then, of course, as we move forward and as the transformer architecture was being developed on the language side, right, on the NLP community, then it was, at some point, not surprisingly, adopted by the computer vision community as well and applied to visual input as well. So you have already learned how transformers work and so on, and basically the move from using transformers in text to using transformers in vision is not a very big move, right? So essentially, what is being done here is, again, splitting the image into patches. So now we don't go by regions of interest anymore because the transformer is so powerful that in principle it does not need that. So the image is arbitrarily just broken down into patches, right? And then these patches are embedded, right? So, and then they just are considered like visual tokens, basically. And these visual tokens can act as the tokens that we have in language and then be used by the transformer blocks. Okay, and then, yeah, so typically this is also pre-trained on object classification, right, using the initial systems, and then fine-tuned for other types of tasks, okay? And even though we have this broken down of the patches that are quite arbitrary, not very informal initially, due to the massive attention mechanism and context dependence and so on of the transformer, actually it looks like the spatial and contextual information that is pre-trained by the visual transformer is stronger than what we can do with the CNN, even if we are using regions of interest, all right? Okay, so using these kind of methods over the years, from 2015 deep learning revolution to when the visual transformer appeared in 2021, it's clear that we have some rather powerful methods for representing visual information, right? So, all right, so we can use these methods that are coming from computer vision, and we can apply them to these different tasks that have more interest from the point of view of the NLP community, right? Because we are still dealing with this kind of task-specific setups where we are interested in solving a certain task. We'll move later to the other types of approaches. Well, in any case, we always are going to need data sets to learn from, right? But let's look first at data sets that were originally developed for tackling specific tasks. All right, so what are the data sets that we can use now that we can represent both language and vision? Then how can we learn to actually put these two things together? What kind of data we need to learn to put these two things together that are a bit more language-oriented than ImageNet or Vision Genome and so on? So the most classic data set, maybe you've heard about it, I don't know how much interaction you have with multimodal work or not, right? So it's the COCO data set, the Common Objects in Context data set, the MS COCO data set, and this is a data set that also has been updated over the years and so on, but it's a data set of image captions. So there are a bunch of images, and then several descriptions, captions for these images were crowdsourced. Right? So I think that there are at least 5 per image provided by different people that were just asked to describe what is going on in the image. Right? So then this gives us data for images and full sentences, not just categories, but just full sentences that describe what's the content in the image. Right? So this kind of data should be useful for learning what are the cross-modal interactions between vision and language, and in particular for developing models that actually do image captioning automatically. This was extended also, for example, to multiple languages at some point. There is the multi-30K data set. There are also other data sets. I will mention some others later, right, where you have, in this case, translations of some of the original English COCO captions into other languages. So then we have parallel data together with visual information, right, which can be used for image captioning as well, but also a bit related to machine translation. Okay, so given this kind of data of images annotating with captions, now the point would be to develop a system for image caption, right? And as I was saying before, so image caption can be operationalized as an encoder-decoder type of task, right? Where we want to encode the image, that's our input, and we want to produce a description of that image in the language modality, right? So it's a language model condition on visual information. So this is a standard type of image captioning architecture. We encode the image, for example, using a CNN, but we can also use a visual transformer, right? We can encode the image using a CNN, and then we use the final layer, the final visual feature to initialize a decoder language model, for example, to initialize an LSTM or another type of language model, right? So this is the main the main type of architecture, which should come as something very familiar and kind of just a multimodal adaptation of other things that you may have seen, right? And this basic architecture, of course, can be enriched with different things, right? So many people have enriched the architecture with in different ways. So for instance, we can enrich it with regions of interest to have more specific type of descriptions, right? So there are other architectures that are a bit more complex that still have the main CNN branch here, but also extract regions of interest, and then they fuse these two types of information. One is more global, the other one is more local, and this is what is used to initialize the language model, the decoder language model, right? So this is a possibility. And of course, we can have attention mechanism, for example, attention mechanism over the regions of interest, right? So this would be a common thing. So we have several regions of interest that are just produced by this region network. Not all of them are equally important because not all of them are equally salient. So with an attention mechanism, and the training signal that comes from the ground truth captions, and we can learn what's the right attention over these regions. All right. So yeah, so they can be enhanced in different ways, and this is one possibility. And another possibility is also, which is something that we had done in the past, is, for example, also to enhance this kind of architecture with information that may come from human gaze, from how humans are looking at an image when they try to describe it, right? And so can you tell me why you think that this what could this add? What could we gain from doing something like that? Okay, so gaze can be a form of, it's the human attention, for example, okay? Yeah. Okay, first here.
You get grounding between the text and the exact object.
Okay, it's a bit more complex than that, but yeah. Exactly, I'm hinting at this here, right? Yes. Yeah, so, okay, all this is very interesting and all this is true, right? So first of all, in computer vision, already gaze was used to create saliency models, right? So you would just aggregate, you would have people with eye tracking looking at the images and describing them, and then over a set of people, you would aggregate the fixations, and that would give you a saliency map. And that can also be helpful for figuring out what are the relevant things, right? Then you were saying about grounding. So you can say exactly when people are saying this, they are looking at that. I mean, that's great. There is a caveat, though, that actually how the two modalities in human processing, right, in human image description, how the modalities interact is not very simple, right? It's not exactly that we look at the stuff and we say it. So it is quite complicated. Usually, we tend to first look and then say it later, but also not in a completely linear way, right? So actually just studying this cross-modal alignment in humans is very interesting because it can give you insights on how best to design an image captioning system, right? And then over there, the sequentiality was pointed out. And yeah, I think that this is quite important. So the approach that we did here has to do with sequentiality. So it's the fact that if you have a saliency map, in general, as I said, this was aggregated over several individuals looking at the image, and you have a saliency map for an image. But actually, describing an image is a sequential process, right? So you're not looking at the same place all the time, the most salient place all the time. You are looking at different places as you are describing. So like this is what's called scan paths for eye tracking. So these scan paths are sequences, right? So one possibility is to, okay, can we exploit this sequential information that in principle is richer than just a simple static saliency map for an image, right? And so this is what we did in a work that we published in 2010, right? And the idea was that we can, so we have, I'll show you in a moment the type of data that we have, but we have information about the fixation, so where people were looking when they were producing each word, so in terms of, may not be super indicative of grounding, but we have this alignment between the words that are being produced and the fixations that people are having, right? And then what we did is that we can input at each time step. We were using an LSTM at the time, and each step of the LSTM, we can give that information. So that, in principle, is more precise information that is relevant at that point, right? So this is sequential, while this is static, even though the fact that it's static, as I said, because we can use an attention mechanism over the regions of interest, doesn't mean that it's constant over all time steps, right? So this may vary as well. But the idea is that using the gaze information may give you a more powerful type of signal. Right, so in this work, we were using this data set it's a Dutch data set, where people are where people are looking at images and they are asked to describe them, in this case in Dutch, and they are wearing an eye tracker, and the eye tracker is recorded, and there is an alignment between the speech and the, and these fixations, the eye tracking, and there are also transcriptions. We were not using directly speech in this case, even though that would be also very interesting, but we were using just the transcription, so aligned transcriptions with the eye tracking data, right? So this is the paper that I'm mentioning here. Yeah, so I already said maybe the main things. I don't want to go into the details, right? So we were adapting an existing image captioning architecture by checking how much we would gain from inputting this kind of more like gaze-guided type of attention, okay? And well, so we see that there are some improvements with respect to some measures, right? But then, for instance, what we see is that this, qualitatively looking at the descriptions, that this gives rise to descriptions that are more specific and that we could qualify of more human-like, even though you will tell me whether that is good or not, because sometimes they look like this, right? So, for example, we see, okay, at the bottom you have the reference, so this is what the human had produced. There is a transcription in English as well. So for example, for that image, one of the humans had produced a bakery with a rack with a lot of donuts, right? If you use the system without gaze, then you get something like that, a woman who's standing in the kitchen. If you use gaze, you tend to get things that are more specific, right? So for instance, mentioning the donuts that are there, because that was a point of fixation, right? So that seems to give rise to mention things that are more specific. Something else that happens, because this is a spoken data set, right? There are also these fluences, things like hesitations, etc., like, and so on. And it turns out that then the system is learning from that data, and it's also producing that. When we don't use any gaze information, it's not producing these fluences, right? So somehow that gets filtered out, and maybe that's what we want, because do we want a system that produces these fluences? That depends in which context, perhaps, how natural the system should sound, right? But the fact that it produces these fluences when using the gaze data, I also find it quite interesting, because these fluences can be an indication of having uncertainty over the image, right? So in this case, for example, is an image with lots of things all over the place. There are some pigeons flying, but it's a street, nothing is too salient, right? So you can see how that may give rise to some uncertainty about how am I gonna go about describing this image, right? So, and the fact that these fluences are being produced and that the humans produce some of these fluences as well makes me think that the model succeeded, at least to some extent, in capturing the intricate alignment between the two modalities, right? So if there is uncertainty on the visual side, that's also reflected on the linguistic side, right? Okay. There are many more like observations and results in the paper. I don't want to go into the detail. This was just an example of how the main vanilla type of architectures for image captioning actually allow for different types of improvement, of testing different types of hypotheses, etc. Right? And it can be quite interesting. Okay, the other classic task in vision and language is visual question answering, right? So image caption and visual question answering are the two kind of trademark tasks. So in visual question answering, rather than just having image, visual data as input and text as output, in the input we have already two modalities. So we have the image and a question that is expressed in language, right? And then the goal is, again, to produce language, right? So the input image is the image and the question. And as I said, this is more classically tackled as a classification task. It means we are not generating language in this case, even though, of course, nowadays that is being done as well. But the original methods were just designed as classification tasks, where because these are also simple questions, right? That just require a word or yes/no questions or a word. So these are treated as classes, and then the neural network in the end is a classification task, right? And yeah, so the original VQA data set You have some examples here, 600K image questions per. You can see that all these data sets are quite small, right? So that's how things were going for doing supervised learning, right? And the architecture, again, is an architecture specifically designed for VQA. It has many similarities with the image captioning, right? So we encode the image similarly to how we would do it in an image captioning case. And then we also have an encoder language model. We encode the question, and then some method for fusing these two modalities. There are different types of possibilities that people have tried, right? From multiplying these vectors to projecting them in the same space, etc. Right? And then in the end, a classification layer with softmax over the classes. Okay, and yeah, like with image captioning, this could be enhanced in many different ways, right? By adding more powerful submodules, etc., right? And eventually, of course, nowadays, by using pre-trained models here, right? So rather than using possibly LSTMs here, so obviously using like generative LLMs and using visual transformers, etc. All right. Okay, there are a few other tasks that are a bit extensions of these two main tasks. And there are many others as I mentioned, but there is no point in listing all the tasks, but I just want to mention a couple so that you see a bit the type of varieties of tasks, and I'm sure that you could also come up with other tasks yourselves, right? Like, for example, visual storytelling can be seen as an extension of image captioning, right? But in this case, the input is going to be a sequence of images, and the output is going to be a sequence of sentences that are related to these images. So at some point, in 2016, this VIST data set was collected, the visual storytelling data set, which has this form, right? This is how it looks, right? And here, this example here makes the point that, well, when you are producing sequences of sentences for sequences of images, that actually is not like image captioning. It's not like one image captioning after the other. There is a narrative type of aspect, right? So you can see here at the top, these are just image descriptions in isolation. If you just see this image, this would be what you would find in Coco, for example, right? But if you aim to do it in a narrative way, then you have different types of descriptions, right? So that's why it was considered justified to have this different type of data collection, right? So here the images were taken from the same Flickr album. There is no guarantee that they actually make up a coherent story, but they are somewhat related, and then it was up to the annotators to find whatever coherence they could. Some of them were better than others in finding this possible coherence, so it's a creative type of task. And this is an example that is present in the data set, right? How to model it? Well, very similarly to how to model image captioning. But of course, you may think of enhancements that you can use here and there for trying to capture the context, for example, right? Attention over the images, for example, right? Or, different ways in which you can maybe hierarchically represent the linguistic context, right? So all sorts of possibilities, but essentially the same type of encoder-decoder task from visual information to linguistic information, right? More extensions, perhaps this one more similar to VQA in this case. There was at some point a trend on visual reasoning. That's still something, that's still a thing, right? But on trying to figure out whether the models that had been developed for VQA with the VQA dataset and so on, whether they actually were able to reason over what was happening in images, right? A bit more logically related reasoning. And a couple of datasets were created. Some of them were synthetic, right? Because that allows you to have a lot of control on what's in the image. If you want to figure things out, like there are exactly 3 squares not touching any edge. So in this case, we have, in this data set, the natural language for visual reasoning data set, we have a set of images, so you also have to reason over different images. And this is just a true-false task. So it's a bit like a VQA, where the answer is just true or false, right? So you have, it's a very image verification task. So you just decide whether it's true or false. And the idea is that in this data set, this requires some kind of logical reasoning, right? An extension of this data set, an extension of the task, slightly different, was also done in the end with actual photographs, with naturalistic images, right? And in this case, the task is more about saying whether this sentence is really a true sentence given the two images that are present. So it's a slight relationship, right? But yeah, so the point of this, as I said, was to try to have a better understanding of what were the reasoning abilities of the models, right? We also developed a data set in this line using synthetic data. And our focus in this case was on objectives that are context dependent, that may mean things in different contexts. And the classic examples of these adjectives are like gradable adjectives, right? So for example, when you say that something is big, well, that depends. That's going to be big depending on the context, right? In some contexts, it will be big. In some contexts, it will not be big, right? So here we are just playing with geometrical shapes, but of course, this is very relevant. And in other data sets and in other tasks, these kind of objectives that are context dependent were just treated as categorical. Big meant this many pixels, right? Not exactly like this, but they were treated as categorical, but of course, these are in fact context dependent. And we wanted to investigate to what extent the models could learn the context dependence. It's a bit complicated to explain here quickly, so I will not, but I wanted just to give you the reference. So this is a much more targeted task for analyzing the linguistic capabilities of the possibility of a model to learn these linguistic capabilities that are a bit more intricate to what we typically look in these models, but for words that are very often used, like, like big, small, etc., that are present very often. All right, so yeah, extension of VQA with yes, no answers, true, false answers. Another extension of VQA is, well, why don't we try to move to multi-turn interactions, right? So VQA is a bit like a dialogue, but it's just a one-off, right? So one question, one answer, so you don't have more interactions than that. Typically, that's not how we interact. Of course, there are many useful tasks that you can do with VQA, just one-shot answer, and so it's not that it's not useful, but we may want more extensive dialogues with more interactions, with more questions. So there was also a line of research in trying to develop models, trying to develop data sets and then models that would exploit those data sets where the interactions would have several turns, right? So here there are a couple, like for example, the visual dialogue. These two come from the computer vision community. So yeah, I'm not sure. So I've tried to always put the conference where the papers are published, because I find it quite interesting to see a little bit when a piece of work has come from the NLP community, so that would be ACL, EMNLP, NACL, etc., and when it has come from the computer vision community, like CVPR and CCCP and other type of conferences. So this comes from the computer vision community, right? I'm saying this also because these dialogues are super simple, so it does come from the computer vision community. Okay, so the visual dialogue was a first type of data set here, where you had an image, and rather than just having one question, then, by the way, no offense to the computer vision community, I'm sorry. I see here some, no offense at all, right? So I'm sure that I'm also making so many horrible simplifications about visual data that please, you can criticize me as much as you want, right? But I come from NLP, so that's it. We can talk later if you want. So, right, so here we have several questions about an image. In this case, the questions are not restricted to yes, no. The answers are not restricted to yes, no, and the questions. So there can be several kind of questions. And this type of data can be used to operationalize different types of tasks. And indeed, there are different types of tasks that have been used, right? So one possibility is just answering the questions, right? So the model so like a VQA model, but in this case, rather than just having the question as linguistic input, you have the dialogue history, so you have to process a more extensive linguistic context, and that's the point. Or you may also use image retrieval, so the model may not have access to the image, and just by having access to the interaction in language, then the final task may be to retrieve the image from a database of images, okay? So these are other possibilities. Other data set, the guess what data set, in this case is about localizing a target object in the image, right? So several questions are being asked to try to find out what is this object. So this is crowdsourced, right? And then you can model different aspects here. So typically you will need some sort of oracle model that will provide you the answers. But one task can be, for example, try to learn to ask informative questions. Now we are getting into the realm of other type of models that might include reinforcement learning, for example. right? And then finally locate, given the dialogue history again, locate what is the target object that we are figuring out here, right? And again, this also could be a classification task, right? Over the possible objects that are present in the image, okay? So yeah, multi-tone interactions. I also wanted to mention another data set that we created in this vein as well for having more multi-tone interactions. And here with my NLP bias, I would say, and dialogues that are a bit richer, but we can debate it, right? So in this case, one of our goals was, well, let's try to not be so strict about these questions and answers and have dialogues that are a bit more open, where people can sometimes ask a question and sometimes do something else, right? And so in this data set, this is a kind of game like the others. The participants, there are two participants, obviously. The participants see a set of images, and some of these images are in common, and some of them are not. And they are free to talk as they want to figure out which images they have in common, right? So the dialogues look like this. Okay, hi, do you see a white cake on multicolored striped cloth? Maybe that's an answer immediately. I see a guy taking a picture. What about you? Well, the cake is a construction. Yeah, I don't see the cake, but I see the guy. I think this is not he, right? So this is the kind of dialogue. So there are sometimes acknowledgements, sometimes answers, sometimes clarification questions, etc. It's not supernatural, but maybe it's a little bit more, a bit richer, right? And so this data set can be used in different things. And one of the aspects that we were interested in was in learning how it makes sense to refer to a given image given the context of a conversation, right? So the participants were in the process of this game, they were encountering the same images more than once. So they had to refer again to the same image, right? And when we do that in conversation, we typically don't always say the same thing. We try to be a bit efficient. And we kind of tend, for instance, to reduce how we are referring to something because we have already referred to it in the past, and we can build on what's called our common ground to identify things quicker, right? So for example, here you see how two participants in this game may first refer to a guy taking a picture, then later on maybe they call it a guy with a camera, afterwards also a guy with a camera, and in the end it just becomes the camera guy. Right? So it's a way of more efficiently referring to this type of reference and to this image, right? So of course, a classic way of doing image caption, of describing images, it's not going to take this into account. The fact that the way in which we describe an image is actually dependent on how we have referred to this image in the past with a particular dialogue partner. Okay, so just to mention that these were the aspects that we were interested in investigating here, right? So therefore, the models that we developed were taking into account this context, they were taking into account previous mentions to images, and then we wanted to see to what extent they could learn to generate progressively shorter descriptions, for example. Okay? All right. Okay, we still have 15 minutes. How are we doing? Are there questions? Yeah.
I have a question on the slide you showed before.
Yeah.
You have different frames, and then you want to make a story out of it.
Yeah, this is storytelling.
Yeah, here you are. So for each frame, you have some sort of text that can come out if you see it as a screenshot.
Yeah.
And then you want to make a story out of it. So I was wondering if you can actually split this task and just feed to LLM just the different texts from the different frames and ask it to make a story, and not feeding the image at all. Like, can you?
Definitely you can do that. I mean, definitely you can do it, and something is going to come up, and probably it's not going to be so bad. Yeah, I mean, this brings in so many things, right? So of course you can do that, but then this brings the question of how are you going to, for instance, evaluate whether that is a good story? So evaluating what's a good story is just very difficult. I will talk a little bit about evaluation, right? In this case, the point of this data set and the task was formulated as producing a story that is about this visual content. That's how the task is formulated, right? I mean, I think it's yeah. So it's true that you could do that. So you could take maybe maybe I'm just not trying to understand you better where you may be going. So
Just the text.
you could take, but you mean you could take the text like the image captions, right? Okay, right. So maybe what you mean is that you can take the image captions as a proxy for what's in the image. Right, yeah. And actually something like this has been exploited in the past, right? So you can take the captions as a proxy of what's in the image, and that can be the input instead of the image itself, and you can produce a story. Yeah, so that's possible, of course. That's possible. Then you are investigating something else, right? You are not so much investigating whether your model is able to model interactions between the two modalities. You are just abstracting over the problem, the computer vision problem. You don't want to deal with that. You just have the data about the image description.
I thought about this because probably, there are networks that can do image to text and maybe text to text. So I can just combine previous work.
No, but totally you can do that. And as I said, I think that this is justified depending on what is your research question and what you want to achieve. You might simplify part of the task, definitely.
May I comment on that? You can do that, but if you extract, let's say, caption in isolation, right, you don't really know what is important and what is not, what is different. Let's say you may have a ball there. You might not have a reason to say that this is a soccer ball or something else, right? Because you don't have the whole story. So the LLM, the caption model can just extract just a ball there, and then you have no means to understand that it's a different ball from the other.
But that's right, but I was thinking about this approach. Now I was thinking in these classic terms in which this is still considered a supervised task. So you still have the ground truth stories, and you use them to learn. And it's just that you would learn a different mapping, a mapping from captions to stories, rather than from images to stories. But you need the
you
training.
need more fine-grained information, right?
Yeah, you
still
need
the fine-grained information from the visual.
Yeah,
so if you just take captions individually and then try to combine them, you don't really know if the fine-grained information you need is still there in the captions, because
so maybe you're pointing to a different thing. It could be that because you are already abstracting away and mentioning some things that maybe are relevant in isolation, that you don't include all the relevant information. That is possible, and that would be a challenge of this approach. But as I said, I think that you have to have a good motivation for doing that, right? So it may be detrimental for some reasons, but maybe it helps you to have a simpler model, and that's also beneficial. But you probably would be missing some information. That's true. All right, so in the few minutes we've got before we definitely are not going to manage to go to all this, but maybe, maybe let me start it. Let me get started a little bit. All right, so the models that we have seen, as I said, right, so they are task-specific. They were designed for solving a specific task. The data sets were designed for training those models, etc., right? But as I said before, we are moving towards models that are more self-supervised, and that are not designed for a specific task. They can be fine-tuned for tasks, but we just want them to learn generic representations, right? And so I have here a bit of a classification of these models. It's not easy to make them all fit into these classes, but just to give you examples of types of models, right? So some of these models can be considered multimodal encoders. I will show you an example just that is based on BERT. Others exploit cross-modal alignment, just try to map the two modalities into a common semantic space. And then we have the generative multimodal models that are exploiting generative LLMs together with visual context, right? So I just wanted to see a couple of examples of this type of models. It could be that maybe these are the ones that you are most familiar with because these are the most recent ones, I'm not sure, right? So in terms of what I sometimes call multimodal encoders, so what you find initially, so this came up in 2019, for example, so very quickly after BERT, right? So an extension of the BERT model, but with visual information. So it's a mass language model in this case, but it also has visual information in the input. Right? So in addition to tons of text like BERT was trained on, in this case it also uses data sets of image captionings together with the visual information. right? And so here we don't only have the mask language modeling objectives, but a couple of other objectives as well. So also mask region classification. So you also try to predict the regions in the visual content, right? Besides predicting the words, like in the mask language modeling objective. And also this ITM objective that is very common in all these models, where you also predict whether there is actually a match between a certain image and a textual description, right? So you have these additional objectives, and then so you learn richer representations that you can use for different multimodal tasks, like again for initializing an image captioning system or for a BQA system, etc. So this architecture here, this toy diagram is for Wilbur, but there are quite a few systems that came up around the same time that are of the similar kind, this kind of multimodal encoders, Lexmerd, Uniter, Build, and others. Okay. Now, okay, I guess you're tired, but let's go for 5 minutes. All right. So. Then so these are the encoders. Then I wanted to mention some approaches that maybe now they have not become that important, but actually they gave rise to a line of work that has been very influential in the end, right? So this is about like enriching textual representations. So it's about grounding, really, enriching textual representations with visual information, right? And about having this kind of cross-modal alignment between the two modalities, but with a focus on the textual representations, right? So this was an approach from 2020, the Vulcanization approach. I'm not sure whether anyone has heard of it. Anyone at all? Some people have heard of it, right? And I thought it was actually quite interesting at the time, right? So as I said, here the motivation was, I want to have stronger language representations. And I think that it will work if I put visual information in these representations, right? And so here the idea was that we are going to associate with each token a set of images that are related to that token. So really with that token, right? So there is a system for learning these associations, and then we are just going to use this. We initialize it with BERT, and we are just going to keep training on this by having also this Vulcan classification, right? The Vulcan are these images or badges of images that are related to each token. Right? So this was not intended for any vision and language task. It was really just to try to learn representations that are more robust. And they did show at the time that this gave better results in language-only tasks, like, for example, natural language entailment and several of the tasks in GLUE, I guess, right? So in these standardized NLP benchmarks. Right? So we gave more solid representations. These were not the first people that were trying to do something like that, to have multimodal word representations, right? So this was in fact a relatively big trend when the initial pre-huge deep learning things were happening, right? So when word2vec were the types of embeddings that were being used in NLP, then there was already a multimodal fever for some people. And for example, the skipgram model that was used for learning word2vec vectors was also enriched with multimodal information, right? By bringing together the two semantic spaces and having enriched representations, right? So so these kind of approaches are they rely on cross-modality, and they focus more on enriching linguistic representations. This type of approaches that try to bring together representations from language and from vision, in a way, they are a little bit, in my opinion, they are a bit at the base of what later the big CLIP model that was developed by OpenAI did. Slightly differently, of course, but the idea of bringing the representations from vision and from language jointly into the same space, right? So this model, maybe you have heard of it. More people probably have heard of it. Several, yes, many more people, right? Okay. So this is not a generative model, right? So this is just a model that learns from huge amount of data. We don't know exactly which data it's learning from, right? So this is also a problem. And it has two main, it's a very simple model and very efficient model, and this has been the big thing of this model, right? So you have a language encoder, which can be a GPT type encoder, it's going to be a transformer language encoder, an image encoder, which can be a visual transformer, or it could also be a CNN as well. There are different versions, right? You encode the input like this, and you just have a huge data of parallel text and images that you get from somewhere, certainly not only Coco, because that would not be enough. And then you just maximize the similarity of the images and text that are paired, right? So you aim to maximize the similarity, and you aim to and to keep in the space separate the pairs that don't match. Okay, and this can be done very efficiently. And it gives rise to very powerful representations, both at the level of the text encoder and at the level of the visual encoder. Notice, again, this comes from the computer vision community, that this was described as learning transferable visual models from natural language supervision, right? So here the focus was more on let's learn robust visual encoders by supervising them with language. I find this quite interesting because the other approaches are the other way around. Let's learn robust language representations by supervising them with vision, right? So these are complementary, but of course the focus are in different places, right? All right, so we were, we had transitioned into looking at general purpose models, right? So models that were not specifically designed for a particular vision and language task, like image caption and OVQA, but that they were supposed to be learning multimodal representations for general purpose, right? And we saw an encoder, like basically adapting BERT for including also visual information. And then we saw this kind of contrastive cross-model models, such as CLIP, right? Where just by trying to bring together visual and linguistic representations into the same space, it's able to learn very powerful representations, both at the level of the visual encoder and at the level of the text encoder as well, okay? Now, the next type of models that I want to mention, that general purpose multimodal models, would be generative multimodal models, right? So CLIP learns powerful representations, but it's not a generative model. And the BERT, the multimodal BERT is also not a generative model. But of course, now with the rise of generative LLMs, obviously we also have the multimodal versions. And again, I'm sure that in fact you probably are more familiar with these types of models that have come up in the last couple of years, right? So indeed, there are a bunch of generative multimodal models that have come up in the next 2 years or so that are exploiting pre-trained language-only and vision-only models, right? So now these models are available, coming from the NLP community, coming from the computer vision community, and we can put them together to have a generative multimodal model. And so one way of doing this, so for instance, Flamingo was one of these initial models developed by DeepMind, would be so to have an LLM that could be, well, some GPT LLM or Llama if you want to develop something else, right? As the LLM, then have a visual encoder that now, given that CLIP had already appeared by 2023, then you can take not just a pre-trained visual transformer, but actually a visual transformer that has already been pre-trained with CLIP, right, with the CLIP objective. So it has learned these visual representations that have been learned with language supervision, and that can also be more useful, right? So now you can use this and plug it into this generative model, right? And then so you can give as input to this model both visual information that will be translated into visual content, into visual tokens, and linguistic information. This will be, there is a modification of the language model transformer with some attention layers that interleave this information, right? And the objective for this model is, again, next token prediction objective. But some of the tokens will be visual in this case, okay? And it can be used zero shot, also few shot. Like, for example, here's an example from the Flamingo paper where an image is given and this image is described, right? This is a chinchilla. They are mainly found in Chile. Another image, and then another image, and the prompt continues, and the model is asked, given these examples, to just provide a description of this image. right? So just by doing this type of pre-training, the model can be applied in this few-shot manner to describe this image. All right. So yeah, so Flamingo is one of these models. It's a closed model, right? So of course, an important thing of these models is that they need a lot of data because they have many parameters, and we don't know exactly what's the training data. So there is also a trend, like it happens with large language models as well, text-only models, of developing open versions of some of the main closed models, right? So the model Idefix is like a version of Flamingo, but open. So basically, it tries to take the basic architecture with Flamingo, but for instance, using Llama as the LLM and so on, and using Open Clip, which is like a reproduction of Clip, but trained with public data. And so it has the same type of architecture of Flamingo, but it's trained with public data, okay? And this is actually the model that you will see this afternoon in the labs, right? So I think that if I understand correctly, you will use it for VQA, for visual question answering, maybe applying some extra fine-tuning to it and so on. So it's this kind of generative multimodal model, okay? So as I was saying, yeah, so this kind of generative models, like it happens with text-only LLM, they rely on tons of data. So we cannot look at the data sets that I have mentioned before because they are so tiny, they are not sufficient. So where is this data coming from? They need multimodal data, text related to images. So yeah, there is a big push, there's been a big push for creating public data sets. We can debate what is this public, right? But data sets that are really large, so there are some of them. One, for instance, is conceptual captions that was mentioned by Aida yesterday. So this is one of the small ones. I think that she mentioned the 3 million version. There is actually an updated version with 12 million, but still 12 million is not so much. And what we take, these are not curated data sets of captions where you have crowd workers generating descriptions, 5 per image, et cetera, et cetera. This is, how are we going to get this from the internet? Well, the typical thing is you get all the images that you can find, and the alt text that is associated with that image, with those images. Some of them will be more informative, some of them will be less informative, some of them will be toxic maybe or not, I don't know. Right? So you, the data sets are created like this, of course, trying to apply some filters, et cetera, et cetera. And that's how the large data sets that this kind of models require are being created, by harvesting this information from the internet. And of course, COCO, et cetera, they may be used as well. Which may lead to sometimes to some data contamination, perhaps, but we need many more data that is collected in this. Other existing data sets of this character are public multimodal data sets, 70 million pairs of, exactly. So this one actually collects together existing data sets plus some additional public sources in the internet, right? So it's kind of a compilation of existing data sets, like some that we have seen, like COCO Visual Genome, and some others, right? And then another huge one as well that yeah, it's been used for Idefix and other models is this Lion, which also has several versions. And I think, if I'm not mistaken, if I'm not out of date already, then there is a 4,000 billion pairs of text and images, right? From this also common crowd, which is like a full dump of what's in the internet. Right? So this is needed. Creating this huge data is needed for this kind of models. All right. So we have now seen that there are generative models as well, adaptation of the generative language models. Of course, what's another version of the language models? Well, the ones that are instruction-tuned, right? So the more chat-related language models. So instruction-tuned language models also are started to get extended to the multimodal context, right? So instruction-tuned extend to the multimodal space. This is from last year. So this is the Lava model. I would say that this is quite state-of-the-art still for instruction-tuned multimodal models. Yeah, and well, at least for open or semi-open type of models. So yeah, a bit similar to what we have already seen before in terms of architecture. In this case, the LLM is already an instruction-tuned LLM, an instruction fine-tuned LLM. Then again, the clip vision encoder is used. In this case, this is frozen. And then what they want to do is to fine-tune this for instructions, right? So you have it, and you fine-tune for instructions data. But again, the problem of the data. Where do you get data like multimodal instruction data? Again, this has to be created, right? So, yeah, so I think that in terms of the model and the technical, of course, there are a few technical difficulties and so on, but it's basically just an extension, right? The problem actually comes from where to get the data to train it, okay? So how is this data created? Well, nowadays, the data is actually automatically created, right? It's actually created by, generated by ChatGPT and GPT-4, right? So that's where we are going. So we're going from creating data sets as well as we can, they are small, then crawling things from the internet, and then actually just automatically generating them with the language models that we have at our disposal. So here you see the process of how this is done. Yeah, so over there, this is an example of the final data that is then being used for the instruction fine-tuning of the model, and then here the prompt, just in the middle. So the prompt that is being given to GPT for generating this kind of interaction data. Maybe an interesting feature here is that these GPT models that are generating this data actually don't see the image at all. Right? They are generating multimodal instruction data, but without seeing the image, you can see here that the image is just being, so there are the coordinates of the bounding boxes, so the objects that are annotated in the image or that are detected in the image, and this is just given in textual form, in sequential textual form as part of the prompt to a text-only GPT model. Right? And then the model is asked to generate this. And this is what's being then used to fine-tune the multimodal model for instructions. All right. So here are some examples from the Lava paper on the type of interactions that this may allow. Right? So you may give it a photo, and then you can do a bit of VQA, of visual question answering, but then you have the more extensive type of answers that you can get from a ChatGPT style type of model, etc. Yeah. So to generate, so some ingredients in the fridge and what can be cooked with this. Give me a recipe, etc. So basically, yeah, multimodal ChatGPT, a bit like GPT-4o, etc. All right, and then yesterday there was this question on whether there were RAG models that were multimodal, and I said, I don't know, I don't remember, maybe not, right? But actually, yes, now they start to come up, and in fact, I should have known because I remember sharing this paper with my students because I wanted them to read it, and I had not read it myself, right? So that was the problem. But some approaches start to come up with a retrieval augmented generation. So some of the Lava model, generative multimodal model, how can it be extended for answering questions that may require external knowledge sources, right? So this paper, as far as I could figure out, is not yet published. I'm not sure. I think it came up, well, I don't know. I think it came up in arXiv in April, so I'm not sure what has happened since then. But yeah, so this is an approach that extends the Lava model to a RAG framework, where for answering questions, you, in principle, need more information that might not be stored in the knowledge that the language model has acquired during pre-training, and you need some external knowledge sources. So there are here some examples of what these questions may look like. This might not be the most, to be honest, the best example, but yeah, I think they have other examples later on, right? And yeah, so it includes this retrieval module that is called hierarchical because it has 2 steps. So first, documents are retrieved by a clip similarity. So clip is really used all over the place. So you have you have your input image, right? And then a set of documents. In this case, they are using Wikipedia, right? And then by using the titles of the documents and calculating similarity with clip. Right, so clip, you can calculate similarity between images and text, right? Because there is a common space. By calculating similarity, you retrieve a set of relevant documents, and then in the next step, you try to find relevant passages within those documents. In this case, by analyzing just text, the text in the documents and the question. The image is left aside in that stage. All right. And then these documents are just included as part of the prompt, if I'm not mistaken, right? So they are included as part of you give it this prompt, And here you include the documents, and then the model will generate given this, right? So this is an application of RAG. I'm not sure whether this is what was intended in the question yesterday, because if I remember correctly, that question was more about if you have hallucinations or problems with language, can you use retrieval of visual content to help you with that? So if that was the question, this is not solving your problems, right? This is more, you have a BQA scenario, but some of the questions require additional information that you can find in textual sources, right? And then you use these textual sources to answer a visual question. But okay, another possibility of retrieving visual information could be another option. There might already be something. I think that NVIDIA maybe created something like that. I'm not sure. This is super recent, and I might not be up to date. Yeah? Okay, so we've gotten all the way to RAG, right? So all the stages of the different types of models that we've seen for language in the multimodal space. Some further examples of this, where here you can see some questions that maybe more clearly, more convincingly require external information, right? And some cases where things are gotten right and where things are gotten wrong. At the bottom, you can see, so you have the plain lava model without the RAG module, and the Wikilava, which is the RAG augmented module. Okay? So it looks like it can help for certain types of questions. Okay, so this is what I wanted to do at the break, but we are also almost already here. So I wanted to discuss maybe briefly a little bit this issue, right? That has to do with the type of data that all these models require. So think about the data that we have mentioned so far. I already said it before, right? So we have the curated data sets, and we also have this kind of internet crawl type of data sets. So can you think a little bit about what kind of ethical issues could be related to this type of data? And think a bit broad. I mean, I have a couple of ideas. Of course, if you look through the slides, you will see them, so don't look. I have a couple of ideas. There might be more than the ones that I plan to mention. But what kind of, can you think of problems with this data, or, I don't know, different types of, what are possible concerns that data set creators should be aware of, or things that may go wrong, or things that maybe need to be looked carefully because maybe they need fixing or something? I have some ideas.
The data could be biased.
Mm-hmm. Like for what type of bias, for example?
Like we saw yesterday that some language models correlate. Thank you. Some language models correlate like nurses to being female and programmers being male. This could be another issue with photos. Mm-hmm. So that's sort of bias.
Yeah, so the data could be biased. And I guess that this bias in principle could apply to all data, possibly like curated and internet, but maybe internet has more possibilities than this happens. Anything else besides bias, which maybe is the one thing that we think most commonly?
Copyrights.
Yeah.
How we collect them? Are we allowed to have them?
Exactly. When we are going already to the internet, then how can you keep track of the copyright status, the privacy aspects, and so on? Good point. Anything else? That was coming to mind.
Like diversity in the data?
Okay, like for instance, what do you mean?
Yeah, I mean, if you're working with people, like people that are diverse, that have different looks, different...
Yeah, diversity in the data. Yeah, absolutely. Yes. Yeah.
I wonder what is the environmental cost to train something.
Okay, good point. Okay, that's more on the training side, right? On the training side more than in the data set, but of course it's an ethical aspect that these kind of models and all this type of frameworks raised, right? Yeah.
When harnessing historical data from images of the past, the language used is not politically correct anymore, so could be transferred to our models.
Okay, all right. I would maybe group that together with the existence of biases, right? So that you can have, but it's okay. So this would point out certain type of data that belongs to different time periods, maybe more prone to observing some biases. Okay, that could be, right? So, I mean, maybe related to what Anna was saying, to the fact that now we have so much generated data in the internet that you don't know anymore what you're capturing. So, okay, that could be. Okay, final. No, final. You go ahead.
Yeah, I was thinking also illegal material. So,
Sorry,
illegal material or like illegal images. So, for example, I read an article some time ago that in Common Crawl there was apparently some good portion of child pornography in the data set.
Yeah,
so that's quite a big ethical issue, I would say.
Yeah, totally. Yeah. Yes, okay, so there are many potential problems, right? And I will highlight a few that cover some of the things that you've said, but all the things that you have said are possible problems. I just want to show you some examples. And I guess, well, the more general discussion is, all right, so how do we deal with this, right? So do we have methods that actually allow us to solve these problems, or probably this is, well, I think people working on safety and ethics and so on are working precisely on trying to fix this. Of course, someone may have a more radical perspective and saying, well, we just cannot do this because there is no way to fix it. So we have to stop this line of research. So I had listed these points here, but as I said, you mentioned some others, and that's perfectly valid. So one has to do with the data provenance, right? So like, we don't know where data comes from, and this means, for example, that we may not be, we may just not comply with licensing, with copyrights, with etc. With ownership and so on. And also the fact that we call these data sets, they are called by their creators like public data because it's in the internet, but the fact that it's public doesn't mean that there is an explicit authorization that you may use this, particularly if you use it for financial reasons, right, for profit. So all this is a very gray area, how you can use this data, right? So this issue of where the data comes from and whether it is fair to actually use it is an important problem, right? Then data diversity, as well as it was mentioned here, which has different type of phases, right? Different types of aspects that can be covered within data diversity. But one way to ask about this is, okay, is the data representative of the population that you intend to depict or that you want to serve with the model that you train on that data? Right? So is this diverse enough? I mean, it's targeting sometimes just by implication, you just discard a certain group, but not because you actually wanted to discard it, because maybe you just didn't think about it, right? And that's pretty bad, actually, right? So diversity is also important. And then, and then in relation to bias and also the possibility of harmful content like pornography, etc. So this, we could group it into data quality, right? So the construction process, particularly when we are crawling the internet, is very difficult, makes it very difficult to preserve quality in the sense of not having harmful biases and so on. So let's maybe look at some examples. So for example, regarding data diversity. So even with the data sets that have been created, diversity has been very minimal initially, right? Like for example, with the COCO data set, or even the 30K that I presented that was a translation into other languages, right? So these data sets are completely done from a Western perspective, and actually the captions are translated from English, right? So it's really not capturing any kind of cultural diversity. Right? So this really leads to a rather limited type of diversity, and the point that is being made, well, I don't have here the citation, is coming later by this paper, the Marvel paper, is that actually, well, there is a lot of information that is culturally dependent and that we are missing out if we just do something from a kind of mostly English or North American or also European perspective, right? There's this example here, like for example, this kind of things. This is a picture from the Netherlands, and so this anybody is Dutch here? Listen to you, so you know what this is this organ, right? So sometimes there are these organs on the streets that play this music, these kind of organs that you sort of use a thingy, I don't know how it's called in English, to play music. So there is a word. This organ of the, I cannot even translate it, right? So this is a word. But if someone from a, let's say, North American perspective is asked to describe this, it may describe it as an unusual vehicle, blah, 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 right? Okay, this is very biased in a way. It gives a certain cultural perspective, right? So clearly the cultural perspectives give rise to different types of describing things, and we might not be capturing this, and therefore our models might not be accessible or as useful as they could be for other cultures, right? So to try to address this, there have been efforts to develop different data sets that account more for cultural diversity. One of them was this Marble that came up 3 years ago. And then here, yeah, so they really made an effort of including in the construction process really people, crowd workers from several languages and from several cultural backgrounds, right? And from the point where so even when at the point of selecting the images, because also the images that you find in Coco are also from a context that are very North American and European centric, right? Not always, but they are very centric in this way. So basically they had native speakers of the different languages that were being covered, which are from different typological families, right? They were involved at all processes, selecting the images, also providing captions that gave this cultural diversity, et cetera, right? And then, yeah, so the data set is constructed as a visual reasoning task. I gave you an example very much at the beginning with those two dogs. So you have two images and a caption, and the task is to say whether that caption really is adequate for the two images. So that's how it was constructed. And these are just some examples of different languages and where you can see a little bit the cultural diversity, right? So there are some efforts that try to minimize a little bit this problem, right? Another very interesting one with respect to VQA, visual question answering, was, yeah, this was already some time ago. I didn't put here the year, but it's already, I think, before 2020, if I'm not mistaken, right? So VQA, okay, who is this task useful for? Well, of course, this task can be useful in many contexts, right? But I think that one prominent scenario is, for example, a task that can be useful for visually impaired people, right? For blind and other visually impaired people, which actually can benefit quite a bit from getting visual information described in a linguistic form, right? But then the data sets that we had, they were not from the perspective, like for instance, the type of photos, etc., were not from the perspective of visually impaired people, and the type of questions were not so informative for visually impaired people. So there was this effort at constructing this VisuWiz data set, which was done by blind people using images taken by blind people and questions also taken by blind people, and then crowd workers providing the answers, right? And there is a challenge and so on that has been going on for several years, so it's the kind of complement to the VQA data set, right? Which again tries to improve this aspect of data diversity and targeting the groups that may benefit the most from this kind of data. All right, then data quality, what we've mentioned about data quality, right? So just to say a few things, right? So the biases have come up, the toxic material has come up, and so on. And indeed, this is a problem for crawl data, and filtering out all this stuff is actually very, very difficult. And as a result of the models are often trained on data that is very dubious. So there is this example a bit related to the nurses and so on that you might have seen, right? So one way to filter the data is actually, again, by using clip, right? So you crawl all these images and alt tags and so on. And actually, I'm not sure exactly how. No, this was not alt text, right? So this is a test that the researchers are making here, to make the point that they were filtering out the good examples and the bad examples by using clip, right? By using similarity between the images and the alt text. If it was very low, then probably that alt text was not related to the image, so that this leads to bad quality, we discard it. If this is high, we keep it, something like that, right? And then in this paper, they make this point that, well, sometimes actually using clip might lead to some biases, like in this case, you have a higher similarity score for the description that says this is a photograph of a smiling housewife in an orange jumpsuit with the American flag, instead of it's a portrait of an astronaut with the American flag, right? So it's to point out that the methods for filtering the data can be very faulty, right? It's funny, but it's pretty serious, right? Okay, so just some food for thought about the problems that the current paradigms are bringing in, and trying to think about how to minimize them or even solve them or go somewhere else, I'm not sure. Any question related to this? Should we move on to evaluation? All right, so let's talk a bit about evaluation, right? Because I presented the tasks, the models, but I didn't say much about actually how they are evaluated, on how good they are, right? And there are different ways in which they can be evaluated. So actually, sometimes it's helpful to use this classic distinction between extrinsic and intrinsic evaluation that you might be familiar with. It's sometimes used in NLP. Right? So extrinsic type of evaluation is really evaluating a model on a downstream task, right? And sometimes this model has been designed for the task, sometimes not, sometimes it has been fine-tuned for the task, but it can be evaluated for the task, for performance on a downstream task, right? In this case, it would be multimodal downstream tasks, right? But we can also have intrinsic evaluations, which independently of a given task, what we are after here is to try to evaluate the more generic quality of the representations that the model is learning, right? So, and this can be in many different ways. We'll see a couple of ways in which we can do that, right? And we may try to assess also like what are the skills that the models are being learned. So a little bit in this direction, the talk by Aida and Mazzadeh yesterday was a little bit in this direction, right? Actually, I will mention the one of the data sets that she mentioned. Like how can we figure out, so we have these very powerful models that are giving impressive results on multimodal tasks, but we are curious to understand why. So what is it that actually makes them so powerful? And maybe this high results on task may obscure some other problems that we may not see. And it's important to detect them, right? Because we want these models to be robust if they are deployed in the real world. So intrinsic evaluation goes a bit in this direction. So looking at extrinsic first, so just evaluating on the task at hand, right? So let's just consider first this kind of image-conditioned text generation tasks, such as image captioning or visual storytelling, and so on. So often this, like the classic way of evaluating the quality of a caption, the quality of a story, is by using metrics that come from machine translation, right? So you remember that Adonis mentioned Blue as the classic developed metric for machine translation, also Meteor, and there are a couple of others, like Cider, I think, was more directly developed for image captioning. But basically, these metrics just look, so you have a ground truth caption, for example, you have a generated caption, and then you measure how different they are in terms of n-gram overlap and things like this, right? So he produced, right? As he said, and as you know, these are not very good metrics. They are quite problematic. They are quite limited, right? Why was it that they were problematic? Right, okay, they are a bit too strict, right? And on what can be generated, right? And it's basically this problem that the same message when you want to describe an image or to give a story, the same thing that you want to say, you can say it in many different things. That's part of the creativity of language. So we can express the same message in many different ways. So why should we penalize a message that is generated because it's not exactly how the reference has been produced? Right? Of course, it's difficult to evaluate NLG, to evaluate generation. I'm not saying it's not difficult, so it's not a surprise that these methods were introduced, but definitely they are very limiting. So then there have been a couple of methods for trying to improve. So one, which I don't know whether it was mentioned on Monday or not, is BERT score. So like where we actually are looking not only at the n-gram overlap type of thing, but we are also looking at the semantic similarity between the reference caption and the generated caption, right? So we allow for more variability in the generated caption. And then we don't penalize so much if there is no overlap. So this is one possibility. So this tries to address this problem. And for example, we also developed a method when we were working on this paper that I mentioned using eye tracking, right? When we use eye tracking, the sequentiality is very important. So we were really interested in whether having this eye tracking information led to different captions that were in the order also more aligned with human captions, because we were using the eye tracking information from certain speakers, right? So just using BERT and semantic similarity is not sufficient to analyze whether the order also is somewhat similar, right? So this is another possibility of enhancing a little bit this BERT score with penalizing also things for the order, right? So this diagram, yeah, just shows you a bit the penalization. Sometimes the word is identical or it's very similar, but the order is very misaligned. So this was a way to account for these aspects, right? But now, one thing. So these measures like blue or BERT score or this SSD and so on, they only compare the textual part, right? They only look at, I have this caption and I'm generating this, tell me how good it is. And they don't even use the image. Isn't it a bit weird when we are doing some multimodal task? So then here comes clip, again, here comes clip score. So another way of evaluating image captioning is just by calculating the clip score, so the similarity between the image and the caption that you are mentioning. And of course, this is not, by itself, it doesn't tell you much, but what you look at is whether there is a correlation between these scores and the ratings that a human would give to how good these captions are. Right? And I think initially this kind of clip score for caption evaluation was considered, that there was a rather substantial correlation. I don't remember the number right now, right? But so it correlated well with human judgment. So clip score can also be used for image caption evaluation, and you can compare different types of models with respect to how high the clip score is between the captions that are being generated and the images. Okay? So moving away from more n-gram-based type of measures for NLG in the context of visual information. When you have things like visual storytelling, of course, it's very similar to image captioning, but more extensive, and therefore, maybe there are other things that you want to evaluate, right? Because what's the point of doing image storytelling? Because probably the stories, we have seen that they were not like captions, right? So how are you going to evaluate whether you have a good visual storytelling model? Maybe these measures that I mentioned might not be enough, right? And again, it's even more creative, this task. Many type of stories could be good, so super difficult to evaluate what it makes actually a good story, right? So yeah, to try to do this, several people have worked on this, including us, one of my PhD students. And for instance, notions that have been considered important for evaluating visual storytelling would be the coherence of the story, so the coherence between the different sentences that make up the story, right? Okay, of course, coherence is a big word. How do you operationalize it? Typically with something very simple, which just means the probability of the next sentence given the context using a language model. Whether that captures coherence completely, I don't know. Probably linguists will say no. Right? And also the degree of repetition, like you don't want like a generation of a story that just keeps repeating the same sentence, right? So you put like a certain degree of repetition that is not too much. And then of course you want to relate the story to the images, right? So you also want to quantify how visually grounded the images are. Is this a story just the coherent and not repetitive, but not about the images? So you also want to evaluate somewhat the visual grounding, right? I won't go into the details. Our proposal here is to have a measure that still uses the referent stories, but what it tries to capture is what are the general patterns in the human-generated stories with respect to these three constructs here, and what are the general patterns with these constructs for the generated stories, and then considering a model beta if there is more alignment between the generated stories and the human stories. Alignment in the sense they are closer, there is less distance. Okay. Again, you can take a look at the paper if you want. This was just accepted to findings. Okay, a little bit quickly about visual question answering, right? So before we had this image condition text generation, visual question answering includes text also in the input. As I mentioned, this is typically a classification task, therefore this can be evaluated just with accuracy if it is really a classification task. But one thing that has to do with evaluation and with problems with the evaluation setup is that for this to make sense, you want a data set and a setup where the visual information is needed, right? If you can just answer your question, the question just by the question itself, then you are not really properly evaluating a VQA system, right? And what happened with the initial VQA data set that I mentioned before, the VQA1, the VQA data set, is that it turned out it was spotted very quickly that 41% of the questions that studied what sport is this or what sport something, it happened to be tennis. right? So of course, the model had learned this association, and it did not need the image at all to answer tennis. So if you answer tennis, then many of those answers were correct. This was just accuracy. So the results were inflated, right? So this is, again, a problem of the data distribution, right? So there are some biases in this data because tennis is the most probable answer to this question, and you don't need the image. So to try to fix this, the next iteration of the BQA data set really tried to make the classes balanced and so on, right? So again, an effort to try to make it more balanced.
Is this an example of overfitting?
No, I would say that this is an example of bias in the data that gets encoded. Yeah. Yeah, so careful with the data, and you have to check whether your evaluation method, it's not only the evaluation method, but whether the evaluation method really tells you what you want to know, given how the model is being trained, etc. Okay, just a bit more about problems with evaluation setups that can happen as well. So, and that can lead to overestimating the capacity of models because the evaluation setup is not set up in the right way, right? So we also did a study with the task that I had not mentioned before, but the task of like visual advertisement understanding. It's not a super well-defined task, I have to say, but there are a couple of papers that are out there, right? So you have images in this case that are advertisements, where there could be a bit of text and a bit of images, right? And I mean, these are actually interesting images because they have not been collected for anything particular, right? So these are images that have been created and that we are exposed to them all the time, right? And if the ads are effective, then we must process them. And they are quite interesting because you can find objects that are unusual, and you can find also like metaphors and figurative language. So we could say they are a bit more challenging to process by a model. And then, yeah, so they are like an interesting test case for whether models are able to understand this. But how do you actually set an evaluation for figuring out whether a model can understand an advertisement, right? So the evaluation is the problem here. Right? So the way in which this had been done initially was as a retrieval task. So several explanations for what the ad was portraying, right, had been crowdsourced. Right? And then this was a retrieval task. So you give the model a set of candidates. Some of them are positive explanations, some of them are negative explanations. You can see here some examples. And then it's a retrieval task. Given this ad, which is a possible explanation. Okay? So depending on what type of models you're using and so on, then this can lead to huge results. Because of how it was set up, right? So the problem here was that the negative examples that the model was trying to discard actually had been chosen randomly from the data set, right? And then by using something like CLIP, again, by using retrieval, by computing the similarity between the candidates and the image, then you get a 95% accuracy of being able to retrieve the right explanation for that ad. So do we conclude that CLIP understands advertisements? I think no, right? But okay, the paper, I mean, there are many more things in that paper. This is not a criticism of this paper, but just an example of how really designing your evaluation setup is very important, right? So to try to point the problems out of this, we created a test data set, a very small data set, but that really avoided the possibility of CLIP using shortcuts, right? So how did we do that? We just created negative examples that were also very visually grounded, but were not plausible, okay? So things like this. So sorry, because here I'm masking some of the brands, even though you can obviously see them. It might be a bit difficult to read, but you see, so the negatives also include terms that are either grounded in the text of the advertisement or grounded in the visual content of the advertisement, to a similar degree to what we find with the actual true explanations. Okay, so these are adversarial examples, right? And if we do that, then that's a more meaningful evaluation setup. If we do that, then we really see that when we use contrastive VLMs, like the ones here, like CLIP and other similar that I didn't mention before, if we don't do this, if we just randomly select the negatives, the performance is huge, and we may conclude that these models are great. But if we do it in this control adversarial data set trait that we created, then it basically goes to chance level. So they cannot distinguish between these. So they are not understanding us. They are just matching in a more back of words manner. the level of grounding of this possible textual representation with the advertisement. So yeah, so a bit complicated. So you can see here some examples for how by humans it's really easy to spot what's the real possible explanation and discard the ones that are not plausible, even if they are very grounded, while the models get confused all over the place. So again, careful with your evaluation setups. Yeah, this is what I just said now. I mean, more generally, I wanted to make the point that this task is just a bit odd, right? So testing for image understanding using a retrieval task might not be the best way to test this capability. Okay, so in sum, we don't have very good automatic metrics for image condition text generation tasks, including also VQA scenarios. There are some efforts, some of them can be decent in some cases, but it's difficult, so human evaluation is often very important, and you will see that many papers also always include maybe a small study on human evaluation. It's almost a requirement. If you don't include it, your reviewer is probably going to ask for it, and it makes sense. All right. So, okay, we were focusing here on evaluating for a specific task, right? So this kind of extrinsic task type of evaluation. Now let's look more at intrinsic evaluation, where we want to figure out what are the capabilities, well, the quality of the representations of these models that are more general purpose, that were not designed for a certain task, okay? So, because of the discussion that we were having at the beginning, why do we want multimodality, blah, 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 right? You could say, well, if we want it, if we concluded that we want it, right, then arguably these multimodal models should have an advantage over text-only models, right? And as I said before, they lead to big improvements and so on, but do they actually have some advantage that we can grasp beyond the performance on tasks? And then this is what we try to figure out with this type of different, not task-related evaluations, intrinsic evaluations. So we can have different types of tests, different types of intrinsic evaluations. Some of them can be on the representational quality. Of course, difficult to define quality, but often this is done by checking how similar the representations learned by the models are to human representations, under the assumption that more similarity with human representations is better, which we could possibly question that depending on our goals, but that's the assumption here, right? We'll see some examples of this, not all of these ones because I will not have time, even though some of them are really interesting, but yeah, so similarity of representations by models and by humans. And another line of research is more on model skills, like so what kind of skills have these models learned, where do they fail, and this is done mostly by developing like challenge test sets, like for example the one that Ida Nemadzadeh mentioned yesterday, what I will mention. So let's look a little bit at this. Are you doing okay? Or are you fading away? All right, good. Sorry, I feel that I'm going a little bit fast, but and not asking for your input too much, so I hope that you're still there. I'm just trying to make it. So if you have questions, please just raise your hand. All right, so how can we test general quality, like alignment with human representations? So one line of research in the multimodal domain is by looking at attention on the images, right? And we can compare precisely eye tracking data, so where humans are looking with where machines are looking, which is not exactly looking, but where attention is being fixated on the image, right? And so this was maybe the first approach that looked at this, and so this is from 2016, right? So this is a CNN model, of course, with some attention, etc., right? So, and in this case, the correlation was found to be pretty low, right? So less than 3. I mean, a bit debatable whether that's low, because in cognitive science that's not so low, but clearly the interhuman correlation, so how similar the human attentions of different humans looking at the same image were, they were not identical, right? But there was a correlation of 0.6. So, okay, it looks like this attention is not human attention. Okay, not surprising perhaps, but it's good to know. Then there was another study a few years later. This was on VQA, because the previous one was on image captioning, I think. And in this case, this was quite interesting because the eye tracking data was not only over the image, but also over the question, right? So the input here is both image and text. So you can have attention over the image and over the text as well. And what here, the point was not so much whether they were similar, but what they found was that higher correlation with visual and particularly with text attention, so higher correlation between the human and the models, is a good predictor for better BQA performance. Okay, so okay, you can chew a bit on that and what that means, but basically it looks like it might be desirable to have human attention be relatively similar to the machine attention, because because there is a positive correlation with performance. So I think this is quite interesting, right? And then therefore you can compare different models with respect to their level of how similar the attentions are to humans, etc. I think it's quite interesting. All right. Okay, so this was with respect to attention between human and models, a very classic way of intrinsic evaluation that has been applied to text-only word embeddings from the word-to-vec times and beyond, but that has then also been applied to contextualized representations and now to multimodal representations by transformer-based multimodal models, is checking whether the similarity patterns between concepts learned by a multimodal model correlate with the similarity patterns that humans express about concepts as well. So there are data sets that have been collected already many years ago where people are asked to judge how similar are these two words. No visual information here, right? How similar are these two words? How similar are, for example, donut and muffin, or car and train? And the people give a score, all right? You can also take the embeddings of these words and calculate similarity, and then you calculate the correlation, right? So this is a way of checking the human likeness of the representations that are being learned, right? Whether it's a bit like what we are comparing is the semantic spaces that the human presumably has in their head and the semantic space that the model is learning. Okay, so this is a common way to do that. And so we did a study with multimodal encoders, like the ones that you see here, so text-only models like BERT, but then also like BillBERT, the vocanization approach, and other type of multimodal encoders. And we saw that for some data sets, actually the multimodal representations have an advantage. So basically, the multimodal representations are better predictors of how similar two words will be judged by a human, right? No visual information is happening here, right? It's just the representations learned by a multimodal model better aligned with the similarity judgments than the representations learned by a BERT-only model, okay? By a text-only model in this case. So it's a bit, okay, you would say grounding really helps to have more human-like representations. But is this true across the board? Because if we only look at these data sets, it looks like yes, but if we look at another data set of human judgments, then it looks not. It looks like actually a text-only model sometimes is a better predictor of similarity. So it's not really across the board. So what is driving this? In fact, it's not very surprising. What do you think? What could be, how could it be that sometimes the representations learned with vision are more human-like and sometimes the representations learned with text only are more human-like? What could be behind this? The data sets are just pairs of words with a score that a human is giving. These are the data sets, right? And this is just the Spearman correlation between these scores and the cosine similarity of the models. But what maybe I did not explain well, and that's the point, is that the data sets include different types of words, include different types of pairs of words, right? So maybe there are some words where visual information is more important than for others, right? Not all words are the same, right? And that's what's going on here. So what we checked is what's the level of concreteness of the words, right? And so the concreteness is a term used also by psychologists, right? So something is more concrete if you can grasp it, for example, if you can, right? So something concrete could be donut or muffin, while you have also abstract terms, like for example, freedom or dreams and so on, right? These are all parts of our language. We use these two types of concepts, right? And perhaps not surprising, what we see is that the representations learned by multimodal models, but visually grounded models, for concrete words, are better aligned with human conceptual representations. While for abstract words, multimodality does not bring any advantage. In fact, learning just from text gives you better abstract representations. Okay, so I think this is interesting because it's not one model is good for everything, you know? So language is rich, it's diverse, and we use modalities as they best serve us for having useful conceptual representations to act in the world, okay? So yeah, so with this you can gain a little bit more insight on how these models work and where are they useful. All right, so this related to representational quality with respect to how they connect with human representations. And the other type of intrinsic evaluation, as I said, is more about model skills, right? So how can we diagnose where models may fail, even if they are very good at VQA or at question answering with the evaluation methods that I mentioned before, right? So can we figure out what are their weak points? So this, if I'm not mistaken, this may have been the first data set that took this approach. This is a really nice data set from 2017, the FOIL data set. And here, this was for evaluating image captioning, right? I mean, the representations of image captioning models. Well, yeah, I mean, it's 2017, so you cannot do it much more general than that, right? And here you are pairing, so you have a caption that really matches what happened, and then another one, which is a FOIL caption, where you just replace a noun with something else that doesn't match the caption, right? So just the middle one, instead of bird or pigeon or whatever, it says dog. That's clearly wrong. It's some sort of hallucination or whatever you want to call it, right? So the question is, can a model, by using the representations here, say that one is true and the other one is false when you only change this one thing, right? Well, the thing is that at the time, in 2017, models really could not do that. All the different variants of models that had been developed for this, they miserably failed on just this simple task of saying whether this is true or is this FOIL or it's true, right? So this was a very good checkup for how good these models were, right? I have to say that since then, basically this data set has been solved, right? So that's good, we're making progress, right? So now we can distinguish whether a noun has been replaced or not with 100% accuracy, I don't remember now. But so the FOIL dataset is often used as one of the baselines in many measures when you see this kind of work, right? And typically it's a kind of sanity check. Let me see whether the model does well on FOIL, and then I will go into more sophisticated type of linguistic skills, right? So this is working much better now when it comes to nouns. But for instance, what about verbs? This is the data set that Aida and Matsade mentioned yesterday, right? So when we move to verbs, it's not just nouns isolated. It's not that they are isolated, but with verbs, the relationships are much more important. You have the verbs and the arguments, right? So they created this data set, the subject-verb-object probes, which is very similar to FOIL. You have a caption and a positive image for that caption and a negative image, and the model just has to see which one matches, right? There are different ways in which you can do this. For example, you can compute the clip similarity, and then is it higher for the positive case than the negative case, right? Or you can use like the ITM head of another encoder and use it for this task as well, okay? And basically at the time, which is not that long ago, actually. So the models that were available were below chance level for negative pairs, right? So they were not able to detect that was not appropriate for the caption. So tricky. So it's not, even though they can be good at the task, actually they are not processing language as we would expect, right? And this is problematic because it really can lead to some unexpected issues, right, that maybe you are not detecting with a more standard type of evaluation. So there are a bunch of data sets that came up to evaluate this, like the Vinogrand data set. I don't know if you've seen it, was also very popular. So in this case, yeah, so you have images and descriptions and captions where you basically have very similar words, but the images, yeah, you can see it here, right? I'm too tired to describe it, but you can see the point. So there are plants and there is a light bulb, but sometimes the plants surround the light bulb, then sometimes the light bulb surrounds the plants, and then the question is whether the models can really distinguish this. And again, this was very, very challenging for the models, right? So very difficult. We also created a similar data set to test for these things, focusing on particular linguistic constructions like active, passive, coordination, relative close. We chose these ones because these are constructions that children are able to learn very early on when they are learning language, and we thought, okay, so these are basic constructions. Do these models are able to distinguish them? And again, here the challenge is that the true and false captions basically contain the same questions. Basically contain the same words, but the composition is different, right? So the meaning is different, and they don't match with the same visual content, but the words are basically the same, right? So the question is, okay, are the models capturing the compositional aspect of language, or it's just more back of words type of thing? And then, again, I don't have the numbers here, but if you check the paper, you will see that they were at chance level, like CLIP was at chance level, right? And the other models, they were also at chance level. So I think that some of the generative models, let me see what's coming here. Yeah, well, more data sets that probe for different things and so on, where you can see also low scores. Yeah. Okay, I just don't want to go into many details. There is a bunch of data sets. Look at if you're interested, look at the references. They are all probing specific linguistic abilities of the models, right? And in general, the results are disappointing. Okay, to say that they are disappointing. These benchmarks, for instance, some of them have not been tested in the latest with the latest generative models, in part because it's not so easy to apply them to those models, because then you have to prompt them, and then it's difficult to analyze what they produce, and so on, right? But I would say that the general picture that these data sets, these evaluation data sets have been able to unveil, is that when it comes to the meaning of words, so lexical semantics, the representations are pretty good, right? So that's what we saw with the similarity judgment. So they can be quite robust. But when it comes to multimodal compositionality, so understanding the relationships in a sentence and whether that is actually present in the visual content, we are not doing so well, right? And I mean, something like CLIP obviously has not even been trained for doing that, because CLIP doesn't act at the token level, right? So it just tries to maximize the similarity of full sentences and images. So maybe we should not expect that really captures compositionality that well, right? But CLIP is used all over the place, so if we don't expect it, we should also not assume that it does. It may lead to problems, right? And anyway, just for fun, I just got this example the other day. I was in Milos last week for a few days. and then, I mean, I have no idea what Google Maps is using, right? But I just got this searching for this beach, and then there was this, I don't even know how to call it, right? So these reviews and so on. And it gave me an image of a beach with some sandbeds and some umbrellas and so on. I suppose there is a cluster of images that are related to that, and then a cluster of reviews that are related to that, but in this case, the review actually has a negation, right? There are no sandbeds, no food, drink, water, toilets, there is nothing, there are no sandbeds, but this caption is exemplifying a photo that actually includes, right? So basically the negation is not taking into account. There is a kind of matching of main words, but the compositionality clear is not, and I have no clue what Google Maps is using, but anyway, that clearly leads to some problems. All right. I have a lot of things to say. I'm not sure how we're going to manage. Okay, maybe just to finish up with the evaluation part. So to finish up with the evaluation part. So remember the instruction fine-tune model that I mentioned, right? The LABA model. How do we evaluate that model? That's another, we don't yet know very well how to evaluate them, right? So we have, it's very difficult. We have some standardized tasks, but it's really quite tough. Like, when is the model really following an instruction well or providing a good answer? There are so many possible factors and so on, right? So how is this one evaluated? Given how the data was constructed, you should already have a good guess. The data was constructed, training data was constructed automatically by GPT-4. So how is it evaluated? By GPT-4, right? So how do they evaluate? You know, you make the model follow these instructions and so on. You have all this bunch of text and output. What do? right? I mean, it would be extremely costly to take annotators to carefully check whether it's coherent, whether it's grounded in the... No. So what you do is that you use chat. I mean, what you do, what they do, I'm not saying you do it. You can think about whether that makes sense. Is that you take GPT-4 as a judge, and then you score it for, in this case, for example, helpfulness, relevance, and accuracy. That also would need to be defined, but okay, you hope that somehow GPT-4 knows what these terms are and they are the same that you think they are, right? So yeah, complicated. What did I want to show you here? Yeah, so this is an example of GPT-4 as a judge, what it's saying here. So it's kind of comparing the lava answer to what actually GPT-4 would give. So GPT-4 is evaluating also GPT-4. And then it has an elaborate explanation for why, in this case, the answer by the assistant number 1, which is the lava one, would be better. Yeah, I will be there for you to reflect on whether this makes sense or not. Know what we gain by this. Okay, how are we doing? Because the clock that I have here is not... All right, we have 20 minutes, right? Well, in this final yeah, question.
If we use another language model, not GPT-4, for the judge, would this be valid?
Well, that's a good point. I mean, from the top of my head, and this is not a line of research I have worked on, I would say it would be better, because there is no this circularity, right? You don't know whether the judge is biased towards its own output. But whether it would be acceptable, I have my reservations. Because you really, if you are taking what GPT-4 is telling, what the judge, whatever it is telling you as a reflection of the abilities of that model, you really have a lot of trust on that model, right? And I think that we know that these models, they are, as I repeat several times, they are pretty amazing, but do we really trust them so much as to do that? I think we are still all developing these models, right? So it's kind of, I find it, I'm not satisfied by this. I find it odd. I don't have a good alternative, but you know, maybe it's more about rethinking the whole thing. I'm not sure. Okay. Now, I want to use the final minutes to talk about some new directions, and I will not be able to go into a lot of detail, but I want to at least mention them so that you are aware of these other type of lines that are a bit less mainstream when it comes to combining vision and language, okay? So, one of them is that there are languages that actually are visual languages, right? And this is sign language. So I don't know if any of you is a signer or knows someone who is a signer, but of course this is a language as well, right? And it has been completely neglected within the NLP community. But now we are seeing more models that deal with sign language. And of course here is a great example of how we can apply, we can apply information from tools from computer vision and from multimodal models and tools from language, but that they will have to be adapted quite significantly to be also more diverse and more accessible to different users, right? So there is this, if you look at this plot here on the right that comes from this ACL paper that is mentioned here. So this just shows how in computer science, but it is mostly computer vision, how in computer vision there have been more and more papers that deal with sign language, but this has not caught up in NLP. In NLP, very few. So it's only now, so okay, this one in particular is from 2021 ACL. So now you see a few papers here and there, but so far the NLP community has paid very little attention to sign language. So with the advances of multimodal models, I think that this is a very interesting line of research. I have not directly worked on sign language myself, but at my institute there is the sign lab that is working on this kind of aspects. So some examples of how this can be tackled, right? So there are data sets of sign language that are being developed. They are coming up. There are several, so you know there is data that can be used for training models. So that's out there, and more are being created every year, actually, right? So the data is there. So just a bit of an overview of the possible tasks that one can that can tackle when looking into sign language. So you may want to detect whether there is a sign in a video. So typically the input, it can be different because it can also be static images, but typically the input here would be a video, right? So a sequence of frames, that in the end it's a sequence of images, but it will be a video. And in this video, a very basic task will be whether there is a sign or not. Typically there will be other movements, right? So not everything may count as a sign. So you may want to binary kind of detect whether there is a sign in this video or not. If there is a sign, then identify it. What is the sign that is being used? Also another task is segmenting, like the boundaries of the sign. So sorry, excuse me. So identification is which sign language is being used, right? So like, for example, I don't know, is it Greek sign language or it's Dutch sign language? And then recognizing exactly what is the sign that is being produced. And then possible more downstream task would be, do we want to translate that into spoken language or written glosses? Or what do we want to do with when we have identified this, right? So we may want to do a translation, like write a gloss, or the other way around. We may actually start from a gloss, like an intention, and we want to produce a sign language, right? Maybe we want to produce a post that can be then reproduced by a virtual avatar, or something like this. This is actually very, very useful. So I want to mention that it is very important that any efforts on models for sign language involve the deaf community, right? So to make sure that the needs of that community are being met and that we are not just making up toy tasks, right? Is it really useful to translate into glosses, or is something else that is more useful, right? So just to put it out there. Some examples, like for example at NACL this year, there was a paper on sign language. So this is by the group of Maliha Ali-Khanish. They are doing really great work on sign language. So if you're interested, you can follow their work because this is really nice. This is a somewhat more applied type of work. This was a demo paper, I believe. And so it's more applied, where they are trying to to generate sign language instructions, right? So they are sort of translating, if I remember correctly, translated instructions in text into glosses that then can be mapped into signs, something like this, right? And then these signs, they are not directly generating them. I think that they are retrieving them from a database or something like that, okay? Yeah, something like this. Look at the paper. So this was on, so generating sign languages in a retrieval fashion. And this other paper, just as an example, this is in iClear, so not so much NLP related, but this is more about, so generating glosses rather than generating signs, generating glosses from a sign. Yeah, so using generative large language models. Right? So it's a bit, so you see you have a language decoder that is going to exploit the input features a bit, as we have seen when the language decoder exploit the visual tokens that come from the visual transformer. Here, what we typically have is going to be some graph that represents the pose, right? But it's also a visual type of information, right? So I didn't go into the details on how you can represent this type of visual information, but usually you start from a graph, even though you can also use the pixels directly. But yeah, it can be a bit intricate, but I hope that you can see how there can be parallels with the other multimodal world. Okay, so, and besides sign language, which is particularly interesting, more generally I wanted to make the point that in fact, even spoken language, the most natural way to use it is actually in face-to-face, right? Like when not sign languages, is actually in face-to-face. And then language is multimodal not only because it's perceptually grounded, right? Which is the point that I've been making all along. Actually, it's multimodal because communicating in language includes other modalities that we use constantly, like all the gestures that I'm doing all the time. Some do more than others. I do quite a lot, right? So gestures are also part of how language is used in face-to-face communication. Of course, in NLP, typically we don't look at face-to-face communication. We look at stuff that is like online, that is in documents, right? But actually, so gestures are there as well. And these I have really become very interested, and I have already done a little bit of work on gestures, which is a bit of a departure from mainstream NLP. And I find it really interesting. There are many types of gestures. Some of them are emblems, like for instance, when we do something like this, right? Or beat gestures, which is what I'm doing, that I'm kind of punctuating my prosody and so on, and marking a bit my discourse structure with my gestures. And some others are more representational gestures, like iconic gestures, where you try to say something, right? Like, wait, there is a block in this transformer, something like that, right? Where you try to represent something. And so gestures also develop sequentially, right? They don't just appear. Maybe the emblems appear a bit more, but they always develop sequentially. There is this preparatory phase where we are moving, then the main meaning-related phase, particularly for representational gestures, and then a retraction phase, right? So if we want to identify gestures and represent them, we have to take into account these properties. So some work that we've done, this is with S.M. Galeb, a postdoc that now has moved somewhere else. So we try to learn gesture representations that were robust in a self-supervised way by exploiting the skeleton graph, the graph of the skeleton, and also the speech that was being produced while the gesture was taking place, right? And we use a contrastive model, so a bit similar to, well, it's not like CLIP, it's more like Lexmert, but a contrastive model that just tries to bring together the graphs that correspond to a gesture, augmented with different views, so they should be closing the space, and the speech that is being produced at the same time of a gesture, we also try to bring it together in the same representational space, right? And then we ask, okay, these gestures representations that we are learning like this in this type of multimodal model, are there any good? So again, difficult to evaluate because we are not dealing with a certain task. We just want to learn gesture representations in general. So we have to evaluate them in some way, and so far we have only evaluated them intrinsically. We have plans to do this extrinsically as well. But just to give you a bit of a feel for how this can work, we can have hypotheses of this kind. For example, we hypothesize that if these representations are any good, then the gestures by the same speaker will be more similar, so two gestures by the same speaker will be more similar if they are referring to the same object, right? So before, they were referring to this bar, right? So if they refer to the same object, they will be more similar than if they refer to different objects, right? That stands to reason, I hope, right? Is it the case? Well, okay, it's the case. It's not, the correlations are not great, but we see that it is the case, right? Or another hypothesis. So the representations of a gesture that refer to the same object will be more similar if, well, now I'm getting messed up. Well, you can read it yourself. I just can't. I hope you can then look at the slides carefully because I feel that I'm rushing so much, right? But anyway, you can have some kind of theoretical or common sense motivated hypothesis of when two gestures should be more similar to the others, and then we can check whether your representations are really according to those patterns, okay? Just apologies. All right, I just, you look at it yourself. Okay. Yeah, there are some models out there that are also dealing with gestures, understanding them in the sense of classifying them, but also generating them. And again, you start with graphs and so on. And this was something at ACL this year. So it looks like there is work that is taking place. Okay, I'm going into the end. So thanks for bearing with me. I don't even know the time. We're not doing so bad. It's me who's doing bad, not the time. Okay, I'm coming to the last slide, yeah? So, given this kind of landscape, so what's the future of multimodal NLP or vision and language NLP, or I don't know. So what can we see in the future? I don't have the answer about what's the future. I'm sure that you have ideas of your own of where we are going, but some things maybe are not that difficult to predict, or at least we see that it's going there, right? So, okay, it looks like we are going towards very big foundation models that can simultaneously produce and generate all sorts of modalities, right? Like images, text, speech, code, action. We are already seeing some of these models. Most of them are closed models, so we don't quite figure out exactly how this is being done, but it looks like this is This is a tendency, and probably we are going to see more and more of this. And there will be lots of research questions of understanding how this is possible. Is, for example, scaling the data better for these models as well? You know, so I'm sure that there will be tons of research questions as well. Now, I would hope that within NLP, there is more and more attention to more natural language, right? So there is this, I'm gonna put this, so there is this paper by Jegos Shrupala putting natural in natural language processing. This one is arguing for using speech in particular, because language is mostly spoken, modulo sign language, right? So I would like to see this trend of having a bit more diversity in NLP and looking at more natural settings, right? And for this I mean speech, but I also mean like, well, face-to-face communication, like gestures, like being a little bit more towards this natural. And now we have more tools that allow us to tackle these things. So I hope that we can do this, And of course, another line, and I have not talked about this at all, even though it's also very prominent in some sub-communities of vision and language, we also can think of about embodied agents like robots, right? So of course, robots act in the world, right? So you need all sorts of modalities, including action. So with more advances in vision and language, then we can also get to better embodied agents physically, like robots, or also virtually, like avatars that can be helpful also in many situations. And then finally, what about, so going back to the grounding, right? Is all this going to help us to really ground language in perception like humans do, if we want to do that, or to understand actually better how humans ground language in perception, because it's not that it's a completely known thing, right? So there are also efforts about this. So there was this paper published this year by Brendan Lake and collaborators, where they are using a data set with a camera mounted, if I understood correctly, a camera mounted on a child, ethical issues, I don't know. Right, so to see the view of the child, like what kind of multimodal information perceptual information is being accessed when language is being learned, like language acquisition, right? And if you use this type of data, can you really learn, can you model this with certain types of neural networks? And what does this tell us about maybe efficiency, but also about whether you need something innate as part of the language faculty, or whether you can just learn it totally from experience, right? So there are lots of interesting questions that can be answered in this direction as well. I'm finishing, but by acknowledging that, so I presented, so that some of the stuff that was presented in this tutorial was also inspired by some previous tutorial that Desmond Elliott gave at the Lisbon Summer School already for a couple of years. You can check their slides. You will see that that's a bit of a more machine learning oriented tutorial. Some parts are from there with permission, of course. Good friend of Desmond. That's it. And I also want to acknowledge my group members. I didn't put the names, but you can see most of them here because of the feedback that they gave me, and in general, the great work that they're doing. I mentioned some of it in the tutorial, but not all. And thanks to all of you for the attention and for staying put for 3 hours. If there are any final questions, I'm glad to take them. If there are none, I also understand.
So, do you think models that go from text to images, things like diffusion models, could be combined, for example, in valuation? I don't know, when you do image captioning, if you then pass the captions through a diffuser model and get another image. Have people done any work on this?
Not that I'm aware, but I have to say that I'm not completely up to date with image generation, so I wouldn't be surprised. Actually, something just to mention something that we were discussing with one of my PhD students is whether it would make sense to use image generation models to kind of simulate the process that we humans do when we visualize what we are reading, right? So to kind of, anyway, to have a representation of this more grounded or embodied representation of the language, right? So I think that there can be maybe interesting possibilities for using image generation models in the context of other tasks or things like that, right? So whether they could be used for evaluation, possibly. I guess that the image generation models have problems of their own, right, regarding also compositionality, etc. So I think with caution, it could be a line to investigate. Okay, now you're all getting you're all getting into the mood. Well, okay, here and then there.
I have a couple of questions. Here.
No.
Yeah, this thing doesn't work.
No, but, well, maybe I hear you.
Okay, the first question is about image generation models. Like, we know they suck at generating text, like when you have something with text and an image with text.
Yeah.
Hello?
Yeah.
Okay. So image generation models don't do so well when they're generating anything that has text in it, right? An image with text. Is there a way, like, is there work on fixing that, like with multimodal stuff?
So that image generation models can also generate text that is part of the image, you mean?
Yes.
I don't know.
Like, I would assume that, like, with their knowledge of language, they should do better, but they're not. Like, is there some investigation as to why?
Well, I mean, I think that typically they have problems with things that are more, like, for instance, with number, right? With the counting of things and so on. And that in a way could be related to, I mean, the possibility of outputting symbols, right? Like the words as symbols could also be impaired maybe by a similar capacity, I'm not sure.
Okay.
But I mean, I think it is a very good question. I'm just not very, I think that I don't know the answer doesn't mean there is no work in this direction. I'm just not aware.
Just one more question. So I'm not a vision person, and I'm very out of the loop when it comes to data sets. But there was one data set that interested me. It's like called like visual common sense reasoning. And I was wondering if there's any developments that you're aware of.
Say again, visual what?
Common sense reasoning.
Common sense, yeah, visual common sense, yeah, definitely. Yes, there is work on this data set, right? So I think that you have the masks of the individuals in the data set, and then relationship between these individuals and so on. I cannot now immediately point you to a paper, but there is definitely work that is being used that uses that data set. Yes.
Hello, thank you for the great talk. One problem that we have in deep learning is interpretability. So do you think multimodal models are more or less interpretable? Like when they make a decision, does it come from the text, from the image? Can we actually leverage this multimodality to maybe create more tools for better interpretability? Well,
I think this is a great question, and I think they are not more interpretable. I don't think so, really. I think it would be, I don't think they are more interpretable. There is less work on interpretability in multimodal models than in text-only models, and I think we need more of that kind of work. But it's very interesting, the question on whether, because of the properties of multimodal models, we actually may gain some insight that perhaps we could also transport into the text-only models. I mean, it's a good question. In a way, perhaps because they are, after all, more modular, right? Because even the more advanced ones, you tend to have a visual encoder, a textual encoder. Because they are more modular, they offer more opportunities for ablation type of works, right? Or other types of interpretability. So I think it's an interesting perspective on whether they can lead to something. But more generally, they are equally black boxes as text-only models.
Hi. Unimodal LLMs, like typical LLMs, only see text. If we have an LLM that has also seen some kind of visual or audio information, like the latest GPT models and whatever, do you think that they understand language more deeply and more grounded in those domains, like in a more human-like manner than the other models?
Well, I think that I would say that that is possible. right? So I would, because I do believe that this multimodality really is part of the makeup of how we construct language. So I believe that that's possible. Whether they really do it or not would require designing evaluation tests that really pinpoint this question. But I think it's possible. But as I mentioned before, when we were talking about concrete versus abstract concepts, I think that multimodality is not necessary for everything, right? So I would hope that for some aspects of language processing, they are better equipped to deal with it, but not necessarily for everything, right? So yeah, if that answers your question.
Any other comments or questions? Just a note about the multimodal communication. So we do know, decades ago, that in multimodal communication there are signals that are not aligned in terms of time. They convey different messages. For example, gestures, eye gaze, speech, pitch of a voice, emotions. So, so what's your opinion about the future of multimodal models? A few years ago, Jan Lecan said that, okay, we will see a lot of bursts about multimodal language models, but what are the points that we see in the coming months or in the coming years in this context?
Well, I'm not very keen on making predictions of this kind, but I think that you are making very good points, that there's different sources of information, and that's very clear in face-to-face multimodal communication, don't necessarily need to be aligned. They can provide different type of information, not on just being different sources, right? I discussed a little bit this with some of you who talked to me in the coffee break, right? The fact that, for instance, in image captioning and so on, the information of the caption and of the image is supposed to be the same, right? While often what we have is complementarity between the modalities. For example, with prosody is very clear. Also with gestures, well, there is a bit of redundancy and a bit of complementarity, right? So this idea of having, of complementing the information for the modalities, I think that I would hope to see some progress on this, right? And I'm not sure exactly what would be the models that would favor mostly this idea of complementarity, but I hope that we see something that can help on this complementarity, that can help both on multimodal face-to-face communication as well as in other multimodal models. So good point. But other predictions beyond that, I rather don't.
Yeah, thank you, Raquel, for this
Thanks
very
a lot.
inspiring talk.